lot of what we're going to discuss today is not for the purposes of understanding in great detail and dissecting the examples we use, but it's to understand why those design choices, or why those problems occurred, and how the lessons that were learned could move you forward into what you're doing in innovation and in advanced reactor design, or whatever the particular endeavor may be that you're pursuing. As Rachel mentioned, this is part of a 3-day workshop that we've had, and by the way, we're going to repeat that, Rachel, again this fall. Brought some folks along that have been in the industry for, I'm the youngster, let me put it that way. I'm the youngster in the crowd with nearly 50 years. These folks have been around for 70 years in the industry. They were part of a lot of the original work. But we're losing that understanding today. And there need to be efforts, which we're doing a little bit of now, efforts to not put you in a position where you have to make some of the same mistakes that we made. You'll do them a different way. You'll find your own mistakes. But if you can learn from what we've done, okay, and how it can apply generically to your considerations, we'll all be ahead in this industry. I'm really interested in the exceptional interest that I see out of young folks, such as yourselves, who have found that nuclear has a future. If someone asked Per today the question, is there truly a future? Okay? And the answer is yes, there is, but it's not going to happen because we sit back. It's because we are able to innovate, demonstrate, and then develop and commercialize, okay, and make the case. And my background is heavily commercial, along with the Naval Nuclear Program. So you'll see a mix of that as we go through this discussion. And you're going to see it from the eyes of quite often from the eyes of the operator and the management team that operates a commercial reactor. You may recall, as Per said today, where do we learn lessons? Well, where we fine-tuned the light water reactor technology is in the operating plants. We really understand that technology. So we need to make sure that as we move into different technologies, that we understand why we're changing and how we're changing. Because the technology we really understand, and I'll repeat it, is that light water reactor technology. We spend a lot of time finding its problems and fixing some of those problems. On the very first sheet here, and as Rachel mentioned, we've given, and Kathy mentioned, we've given you copies of this so that you don't try to read what's up there. Some of this is pretty dense to read on the screen. Don't want you to spend your time trying to read the screen. I'd rather have you listen to me, even though you may get bored with that. I want you to listen to me, and then you can go back and look at some of this later on if you so wish. Okay. Now these are these plants. That's TMI, 3 Mile Island on the left. Okay. Hence the cooling towers are a little dry on the one side. That's Davis Bessey, the next one over from the left. Next one over is LaSalle in Illinois, and the far right is D.C. Cook in Michigan. The reason these are on this introductory slide is each of them in some way have contributed to this conversation in some very important manner, particularly Davis Bessey. Okay, it has managed to find itself in the eye of the world too many times, okay, much more than it would like, I'm sure. See if I can get this thing to respond. You may not use that. So we're going to take a little bit of a historical tour through some selected fundamental design decisions and the basis for those decisions, where they come from, and not dissect, as I mentioned earlier. So let me set the stage in this discussion. The examples are presented from the perspectives of the technology developer, designer, and the regulator. All of those perspectives are very important. Operating experience is presented from the perspective of the nuclear power station and its operations team, engineering team, maintenance team. As this says up here, as designers, we put together this lovely device. We design it, we commercialize it, we sell it, and we walk away, okay, as a designer. And so the operating plant, the operators have to live with the results of that technology development that we've handed to them. And hence, it's very important to understand it through their eyes of what is this machine that we've asked them to operate. How does the management team look at that? And there's another problem that's occurred in the U.S. industry in particular, is most of the companies that did the original design work for the current generation of licensed reactors in the United States, they may be there in name, but they're not there in memory. That memory is gone. Folks such as myself and others in the back, we're not in the industry anymore, and we didn't write a lot of it down. Paris Point this morning, we didn't write it down. The reconstitution efforts, he was much more positive than I would have been on that. The reconstitution efforts of design, we only covered a certain layer. That necessary to continue to change the design and continue to operate plants. Much of the maintenance activity in a plant today is a result, the maintenance activity becomes a design change because the equipment's obsolescent. Or if you're trying to replace certain parts of it, the level of detail is not there to go in and change the internals on a large valve because that design information is missing. So you're reconstituting, if you will, as you do major maintenance activities on major equipment in the plant. Now, I want to start here a little bit, not because we're going to talk about this very much in detail, I can't, okay? But it's important to understand how this part of the industry evolved. We were trading some thoughts over lunch in terms of how some of the numbers get, the magic numbers that get evolved, okay, out of these kinds of activities. Up in the upper left-hand corner, so-called Task Force 1. I don't know if that's a term you've ever heard before, but that was that's the USS Enterprise, the Long Beach, and the Bainbridge, first of the surface nuclear powered plants. A fleet ballistic missile submarine on the right upper side. And what's important to understand is we are in a Cold War. Now, folks understand in this room what a Cold War was, okay? It's everything but firing missiles at each other, okay? You're building a huge capability to have this mutual deterrent between countries. And so we were developing a weapons delivery platform, not a nuclear power plant to generate electricity. This is a propulsion plant for a weapons delivery platform, which is what these are. We were looking for the answers to come as fast as we could have them come. We didn't have time to develop the way we would develop technology today. So there's some unusual answers that come out of this as a result because you're using judgment. And we'll talk a little bit further, there is no basis for the nuclear engineering world at the time these were designed. It just didn't exist. However, we're moving along, there's money behind it, it's a national priority, okay? So things happen. Things happen much faster than they do in the industry today. We built the Nautilus, and the shipping port plant, which is here, which I'll talk about in a minute, built those in 5 years. Okay, technology development, building the plant, operate, 5 years. Now we have a hard time in 5 years getting anything done in today's world, but we're driven by particular priorities and the need to do it. Shipping port plant, important. It was the first attempt, and it was at the demand of President Eisenhower in the 50s. That the Naval Nuclear Propulsion Program find a way to transfer the technology that was being developed at a very rapid pace into the commercial world without compromising the fact that it was classified information. You're in a Cold War situation, and you're up against an adversary who would love to know why you're doing and how you're doing things, okay? So shipping port in some very important ways, if you ever go back into it and look at it as the first commercial reactor in the United States, fairly small, 60 megawatts electric, okay? But a lot of the technology that was developed early in the naval nuclear propulsion program was basically transferred into the commercial world intentionally through that reactor. Now, we never took that advertisement out in the Wall Street Journal, okay? But that's what was going on at the time. If I go to the early perspectives commercially, now this is again, let me set the stage. How did we generate power early on? Well, it's fossil plants. And we had a particular mentality of how we approached the design, building, operation of fossil plants. That approach turned out not to be sufficiently rigorous that was needed for nuclear energy. You may have heard the term at some time in your background, too cheap to meter. Have you ever heard that terminology? Well, what that was a real misunderstanding of what it really costs to design, build, operate, maintain, test nuclear energy, okay? It's an important investment. It's important for the benefit that can be gained. It's important for the economics that can be realized, but it is a big investment, and it's not too cheap to meter, let me tell you. It's very expensive. So here's where we were. The developer, the designer, the regulator, the facility owner, license holder, the licensed operator. Well, that's kind of interesting, okay? It isn't just the designer that sits there and can decide what things look like, okay? I've got to keep all these folks in a coordinated manner and manage them. So at the end of the day, I develop something, build it, test it, and put it into operation so this licensed operator knows what he's, can operate this thing safely. And the last one is very important. At the beginning of this discussion, the owner's expectations, which were driven by economics, not by safety, not by maintaining a technology, but solely by economics. It's the fossil-fired power industry perspective. Safety was not on his mind. Nuclear safety was not on his mind. And it trumped the regulators' thought process on how you maintain a plant safe. And the other part of that is we had this disconnect going on. The designer says the regulatory requirements are mandatory, no more, no less. I'm setting a stage here intentionally because you'll see why this works its way out in a few minutes. Regulators' requirements, mandatory, no more, no less. The regulator says you're going to comply in a mandatory manner, but without consideration of risk. And the owner says, oh, the safety responsibility is the regulators. We have this real disconnect that we're setting up here, okay? And let me tell you, it came home to roost. Now, as we move on, we can learn the lessons in a very serious manner in the industry. But let me just touch on this before I go on. The successful owner's model. The owner emphasized economics without an adequate counterbase derived from an understanding of the technology. They didn't need to understand the technology in a fossil-fired plant. They were sold the technology, it worked. If it didn't work, they shut it down, they got somebody to fix it. And they had an inadequate understanding of the importance to the operator, particularly light water reactor technology. There's a very important role for the operator. And if you want to look ahead, go all the way to slide 60 and have it available to you, because we're going to discuss at the end of the first couple hours of this discussion what you might want to consider as your design objectives for innovation in advanced reactor technologies. And one of them on slide 60 is don't depend on the operator. Don't do it. He's human. Okay? And two, don't let him mess it up. Don't make it so that he can mess it up easily. We have too many experiences that way. Operators got us out of trouble, and they got us into trouble. Okay? And then back out sometimes. All right? So it's very important to understand the importance of the operator, but that wasn't understood initially, and hence the successful owner's model was slow coming into the industry. We had companies like, and I'll mention one in particular here just for purpose of illustration. I mentioned Davis Besse. Toledo Edison was the owner. Toledo Edison owned a few fossil-fired plants. They bought Davis Besse. It was supposed to be 3 units originally, but it was 1 unit. And they treated it like every other one of their fossil plants. They invested in it in the sense of maintenance and those types of activities, not very deeply. And so they found themselves in some real trouble because they didn't treat the technology different to that technology which they were used to and was easy to get along with. We'll talk about some of those in a minute. But let me bring you into the contemporary world first of all, and the world that you'll be working in as far as the industry perspective today. Now this goes along the lines of what Per described to you. This is where the industry is today. Big transition from those earlier slides. The owner is solely responsible for the safety, not the regulator, not the designer, the owner. Whoever owns that plant is solely responsible for the safety. Leaders in industry demonstrate a commitment to safety in the decisions and behaviors. You remember Per used the term safety culture. Well, that's all that describes. Okay? They keep that in mind. It's very interesting, having worked in a lot of different commercial plants, as to how difficult it is to get folks to develop the questioning attitudes, the approach to the corrective action program that Per described, okay? And get a plant to really have a strong safety culture. The licensed operator is essential to safe operations, and he's the only one, he or she are the only one that can make a decision. Don't lose track of that. You hand this plant to that operator, and it's his or hers. He makes the decisions. As an engineering manager, I could advise him, but at the end of the day, that's where the decisions get made. So as you design these plants, keep that in mind. The licensed operator, and this isn't just the United States, this is worldwide. Okay, the licensed operator is the only one that makes the call. And that's just a management prerogative. It's a very important concept. The regulator solely establishes minimum requirements. He doesn't maintain the safety. He doesn't specify the safety. He only puts minimum requirements in place. Now, occasionally when we're in our regulatory process in the United States, we kind of lose track of that because it seems like it's a very onerous process. But at the end of the day, that's all that regulator is doing, is putting minimum standards in place to ensure the public is protected and the environment is protected. Important concept. The owner must have an arm's length, but a professional and collaborative relationship with the regulator. But he can't say, you told me, regulator, what to do, and I did it. It doesn't work. The owner's responsible. The INPO, which you're having a discussion about INPO separately, are you not, in one of the sessions? INPO was the industry's response to the 3 Mile Island accident, Unit 2, which said we need to be self-regulating as well as have our regulator, because the NRC provides the minimum requirements, right? INPO reinforces the operational requirements, how you run the reactor, how you manage your maintenance system, how you manage your corrective action process, all the things that are integral to the way you operate a reactor. Too bad I can't get that thing to work.
Quick question.
Yes, please.
On the early commercial industry perspective side, we had something about the reactor designer and the initial seller. Where would that fit into this, to the contemporary, where does that fit into the contemporary perspective?
Today, the designer's responsibility, that's a good point, that's not on here. We're going to talk about it a little bit more, but I think it's a good point. I'll put it on the slide. The designer's responsibility is to have a well justified design from a safety standpoint and from an operational standpoint. Well justified, well documented. And we'll talk about some pieces of that in a few minutes. But that's their responsibility on the contemporary level. Okay? Well, now it's working. Now I'm going to talk about management for a few minutes. I promise we'll get into some technical discussion, but I want to touch on some other things to set the stage. And when I speak of management here, I'm speaking of management as people. I'm speaking of management as processes by which you do things. Okay? Management of our system of consensus standards that we do business to, and the regulator is really part of the management process. So I'm speaking very broadly here. This is everything that can influence the way you operate this design that is well justified and well documented if we do it right. Okay? Quick one. I'm glad you asked the question. Now, management, the NRC, we've talked about the NRC and INPO. Management weaknesses, it's an important point here, have been in the root performance issues. And the accidents and events that we have occurred in the nuclear industry can come right back to management weaknesses. And in this case, I'm speaking of process weaknesses, standards weaknesses, and people weaknesses. Okay? And we need to understand as designers where these pitfalls are, or where they potentially could be. Because we're designing a machine to be operated by people. And so you have to be able to, as the engineer and the scientist and the developer and the principal investigator, to understand this is going to be operated by people. And they're going to make mistakes, and you do everything to keep them away from having those mistakes become fatal. Quick run through just to give you a kind of a preview of some of the things we're going to talk about. Now these are management in the sense of operations management and plant management examples where, I'll take Davis-Besse in 1985. They should have gone to feed and bleed. I presume that concept at least generally is understood here. The regular decay heat, basically we lost all decay heat removal in the plant. We should have been in feed and bleed. Management made a decision not to go there. Core is heating up. Okay? We were within 10 minutes of damaging an intact core, just like TMI-2. Okay? Management made a decision not to go there. Why? Well, in feed and bleed, the bleed portion is out through a safety valve, and the safety valve dumps on the floor. We're going to get the plant messy. Okay? And then an interesting thought process. Well, that's people. And what drives them, and what their management expectations have been set. One of their management expectations is, thou shalt not crap up the containment. Okay? So this is people that are doing these things. It's interesting how we react. Premature termination of emergency core cooling through Mile Island. Now this is an accident, which I'm sure you've all looked at in great detail. I'm not going to go through it here. But what really occurred? We had a valve fail open. Not very exciting. Okay? And we proceeded through errors of omission and commission to destroy a reactor. There wasn't anything wrong in the sense of we had a valve that stuck open. We should have been able to recover it. And in this particular example I'm using, is premature termination of emergency core injection. Emergency core injection came on automatically. It was doing the way it was designed. The operators had been trained. And this is an interesting human factors and management problem. The operators have been trained that they didn't want to take the plant solid. And if solid makes sense to you, this is a PWR. It's normally got a pressurizer that's maintaining saturation, or subcooled conditions in the loops. Didn't want to take the plant solid. Now these were naval operators. I'm going to tell a story on the naval side of this. These were former naval operators operating a commercial plant. Naval operators can operate a naval plant solid, underway, critical. They were shut down, and their commercial training overrode their naval training. And so they said, whoops, we can't fill, we think we're filling up the pressurizer, we don't want to go solid, terminate. That was a problem, because we weren't only, as you may recall, without going into detail, pressurizer looked like it was full. Unfortunately, the core wasn't full. Reactor was. Okay. Fukushima, I won't go into detail. I'm sure you had this one beat into you over time, okay? What occurred here? Again, delayed operator actions, a decision. David Spessy, Per touched on this, and we're going to talk about it a little bit more today. But a failure to timely resolve operational indications that led to massive corrosion of the reactor vessel head in 2002 in David Spessy. This is a corrective action process failure, and it's a management failure. As you'll see, and I'll just give you a little touch of this as we go a little bit further, you'll see where every indication was there that should have told you you had a problem you had to go solve, and management did not pursue it. So it's truly a human performance, a management failure. An ineffective use of ineffective use of the corrective action program. Now this gets into a whole litany of issues, which I won't go through with you. But if I translate that thing called 5054F, that's what Per called the design basis reconstitution. Do we know what we're operating? Do we really understand what we're operating? The answer is most plants know, okay, in detail. And that's been rectified, but that was the answer at the time. That's the mid-90s. We had maintenance issues on motor-operated valves. Basically, we had set ourselves up for common mode failure. We're going to talk about that a few minutes from now, okay? And I presume common mode failure, if you don't know, you will by the time we get through this. And basically just a lack of systematic corrective actions and improvement actions that were necessary. I won't read this to you, you got it. But strong regulation is important because we need that objective and independent view. As much as that may be painful on any given day of the week, okay, you need an objective overview that isn't driven by the drives of a company that's trying to make money. There's nothing wrong with making money, but occasionally it takes you away from a primary purpose from a safety standpoint. Key messages. Importance of management actions and what you do. Technology developers need to be mindful of how management strengths can help develop robust technology, but conversely, how management weaknesses can lead to inappropriate compromises and potential catastrophic consequences. And the last one is really just kind of a philosophical discussion that says, if you are working within a design organization, and I want to go back to your question, working within a design organization, are the processes in place? Are the reactions of my management team? Are the lines of communication transparent? So when we have to make a decision on a design attribute, are we able to ventilate it adequately and discuss it adequately and candidly and transparently and come to decisions, the right technical decision? I mean, Per touched on that when he talked today. But it's exceptionally important. This is where management weaknesses can cause you a problem. And you need to be part of that, whether you're the developer, whether you're the principal investigator, you need to be very sensitive to. Now let's set the stage now a little bit on how we did design, and I touched on this and won't spend a lot of time on it. Take a look at the center there. We kind of bootstrapped our way into nuclear technology. You know, we had no experienced personnel. There was no engineering curriculum that covered nuclear energy. There weren't any text or reference books, other than some very fundamental ones that were done that came out of things like the Manhattan Project and some of the early work. There weren't any lessons learned because we didn't have anything operating. Okay? We had to develop the special nuclear knowledge in areas like shielding, okay, and core design. I mean, it just didn't exist. I don't know if any of you have had the opportunity and the pleasure of working with what's called Rockwell, which is the shielding design manual. That gentleman does, I know that. Okay. But it was the first try. A fellow named Ted Rockwell led the authoring of that early in the naval program, because we had no basis for shielding. And in the world of the submarine, okay, remember now, not only the people are operators, that's home. They live there. They live on the other side of the shield wall. They live on the other side of what's called the fuel oil tank for the diesel generators. They live on the other side of that shield. They live with the airborne conditions that exist. So it was important to develop, from a personnel standpoint, an environment where the people could be maintained healthy. And in fact, we did it so well that we had a problem when people came back and visited their homes. They caught everybody's viruses when they were home, because they had no exposure to the day-to-day, because they'd be gone for weeks and months at a time. Okay? Design methods, simulators, and the way we did it, I'm just down there at the bottom, is it was a fairly integrated process, but we were learning as we went. Now, by contrast, okay, we've got a system today to work with it. We haven't exercised it very heavily in recent years, in the United States in particular, okay? But it's there. The fundamental structure, management processes, et cetera. And the modern designer has the things that are on the right. You've got to set up consensus standards. You've got procedures. That doesn't protect you. All that says is we've learned a lot, and we've put a lot down on paper. We have some basic, and we got down there at the bottom, we got well-trained engineers in the field, and that's just not engineers, that's me writing engineer down, but whether it's a scientist, a physicist, whatever it happens to be in your background, that were necessary to make this work. Now let's talk about a couple examples. And this is going to be a strange set of ground rules. Remember where we are. Where we are is we've got the Naval Nuclear Propulsion Program developing a light water reactor technology, which is now going to evolve into the commercial world. Okay? We've made some decisions in the Naval Nuclear Program that are based on things like, it's a weapons delivery platform. Gee whiz, it has to deal with things like depth charges. You think seismic design is difficult, you ought to try design for a depth charge at a submarine. Okay? We had made decisions on what we did that were necessary for the military application of a propulsion plant. Now it's time to evolve that basic technology and engineered process into the commercial world. It's important to ask some questions. And this is just an attempt to ask those questions. If you're going to, and this basically reduces itself to, if you're going to change, make sure you understand why you're changing what was already shown to be effective and proven. That doesn't mean don't change, just understand. And if you're going to adopt something directly, make sure you understand why the choice was made to start with. It sounds fairly fundamental. We missed several times as we went to the commercial world on this very subject, and we're going to touch on some. Fuel cladding. Yeah? Here's fuel cladding for naval reactors. I'm very general. I can't go into detail, but very general. Okay? Things you'd expect. Adequate heat transfer. Exceptional neutron absorption. Structurally capable. Very important. Structurally capable. And we made decisions, remember that depth charge a minute ago, we made decisions on what the fuel looks like and how it's designed based on those needs. Okay? Compatible with the quality manufacturing processes that were available in the industry at the time. We did not have an Appendix B, I'm using the US NRC regulation. We didn't have those kind of processes in place. We had to build them. And corrosion resistance, obvious. And the last one's kind of available on a schedule that supports the need. That's kind of a way of saying if it's not fast enough, make it faster. Okay, I mean, we got to do something now. We've got to build submarines now. We've got to build aircraft carriers now. But when we make that decision affects how the technology evolved in the naval program. Now, so if I talk about fuel, the commercial industry chose zircaloy as a cladding. And zircaloy is a good cladding, that's not the issue. But zircaloy was chosen as a cladding from really very few other choices that we had in the 50s. Okay? And gee, let's just take a look at this. The operating temperatures that the commercial world is going to use are higher than naval experience. We'll talk about that in a few more minutes. Shipping port, which is the kind of the technology transfer platform, had some zircaloy clad fuel rods, but most of it was plate type fuel. Okay? And which is now known, it wasn't known at the time, but today known, that's what the Naval Plants use, again, for structural purposes. Cooling water system chemistry differences. And I'm going to talk a little bit more in a few minutes about the PWRs and the use of boric acid. Naval Plants don't use boric acid at all. So we're going to ask ourselves some questions. Okay, is that the right choice today? Should have been the right choice commercially. The downsides of that are very expensive. So the basis for the choice, the industry, commercial now, judge the temperature and corrosion potential is acceptable. Judgment, not testing. Testing was very limited commercially in this regard. The low probability of severe accidents. Now that's interesting. Now this was a thought process that existed. We'll have such a low probability that it's okay to use this, even though we know it's susceptible, as you well know, under certain circumstances, to accident conditions and result in the release of fission products. Now we're talking about here commercial reactors, large source term. Source term translates to everybody here. Large source term, okay, fission products, compared to naval reactors, small. Small source term, easy to cool. Decay heat, not a particular challenge on a relative basis compared to large commercial ones. Okay? So you could easily go down that list and start questioning them. I'm not going to do that here. I'm just going to leave you with the thought. These are the kinds of questions that we have to ask ourselves. Are we making a decision that's based on the knowledge of why the original decisions were made? Or if we're going to change it, we changed something here. We changed operating temperatures, we changed structure, we changed water chemistry. Did we know enough to make the change? I'll submit the answer was no, but we did it. Okay. And we had problems. And I won't read them to you again, you can read them yourself. We had problems. We learned the hard way in the commercial world. And for a while, we basically, and I'll go to the 80s time frame. We operated our plants we managed our plants so that the fuel would remain intact. Sir?
Phil, you might want to mention that when all this happened, the main computer was selected.
No, that's an interesting point. I didn't put that up there. You know, you are in a particular world of computational capabilities, whether it's the machine that you do it on, or the software you do it with, or the modeling capability that exists. Okay? We were very coarse in what we could do. I hope everybody knows what a slide rule is. I could probably guess that most of this room has never used one. Okay? You've used one. All right, good. All right. The slide rule was a tool. And the slide rule has its limitations, primarily not because it's particularly inaccurate. I can deal with that. Okay? What I can't deal with is I can't do the problem very many times. I can't iterate. I can't keep doing the things I can do with a computer and beat the numbers up as hard as I can to get to an answer that's most satisfactory. I just can't do that. I have to have a very good picture of where I want to go. I want to do the analysis as few times as I can. Okay? And the net result is I miss some opportunities for understanding phenomena that I could better understand today. So you're a much more powerful world. Thank you for bringing that up. That's good. Good point. Now, we're working on improved fuel cladding. I'm interested in anybody here who might want to join. Why now, 60 years, 70 years downstream in the light water reactor industry, are we now going to work on an improved cladding fuel? Why are we doing that today? What's changed? Physics hasn't changed. The accident phenomena haven't changed. We've had more experience, obviously. We've damaged a few reactors. Why is it time now to do this? Why do we think we're doing this? Sir?
I'm assuming it's because of stuff like Fukushima, bringing more attention to these things, bringing more attention to nuclear safety in general.
And that's part of the discussion. But that Fukushima, from my perspective, if I look at it, and it's all where our backgrounds are, obviously. If I look at it, we already damaged a core badly in TMI-2. We did that years ago. You're right. I mean, that's what brought it to a lot of people's attention was Fukushima. But the answer is we've destroyed a reactor before. Please. I'm sorry? I don't know that that's driving it. I don't think so. I don't believe so. That one I hadn't thought of that, to be honest with you. I don't think that's driving it because they tend to go with the current license basis. Okay? I'm sorry? Well, that's an interesting suggestion. All right. Have we progressed sufficiently? Would be the question I want to ask ourselves again. In our understanding of some alternative materials. Now, I don't know if I'm not in detail knowledgeable here, but I want to take your point and just play with it for a minute. Some of the techniques we're looking at for accident-tolerant fuel use carbide-based cladding. The Germans were working with the carbide-based cladding back in the early 60s. Okay, so we didn't have today's technology. We didn't have the TRISO fuel development, for instance, for the gas-cooled reactor, or for applications to molten salt. Okay, we didn't have that level of qualification, but we certainly knew about the technology. The technology was there, and it was in a reactor called AVR in Germany, and THTR in Germany. And I don't remember, but I think it was also in the Dragon reactor, if my memory is correct, which is the UK reactor. So the basic carbide coating concept, clad concepts that we are looking at here existed. I'm not going to give you a good answer here, by the way, okay? It bothers me, because this is one of these examples where we adopted the use of something of a particular cladding concept that was utilized in this case, the Naval Nuclear Propulsion Program. We took it into the commercial world, we made a bunch of changes, and did we ever think hard enough about whether or not we should have changed? I have an opinion, others will have an opinion, but the issue is that's a question you want to ask yourself. As you try to adopt using technology that's already developed, make sure you understand what it was developed for and under what conditions the decisions were made to utilize it, okay? And I think we drove by this one.
Also, just part of the answer has to do with the manufacturing of silicon carbide tubes and channels. It's very different.
You're absolutely correct. You're absolutely correct. And so the capability to do it exists today, which was harder to do. It was more of an art than a science back in when the Germans were doing this in the 60s. Sir?
And just to answer the question about whether we've got lifetime extension, that's true for some of the accident molecules, not the whole family, but certainly some of them. So, for example, a lot of the advanced fuels programs pre-Fukushima that the DOE were looking at, including things like high-density fuels, so nitride fuels and so on, and that was about including lifetime extension.
Very good. Thank you for that background. I didn't have that. Thank you. Oh, by the way, it's going to be a difficult task. You better do this really well. What we're asking now, if we're going to take advantage of this, And if we want to apply it to the existing reactors, now you got to go out there in the fleet and convince these owners that there's a reason. Now, the regulator could impose it. That's one route. Okay, that won't go down really well. The other part of it is there an economic advantage? Well, I can pretty quickly show that I can absorb the results of an accident in its infrequent occurrence, and I won't make a decision on that, whether I use this fuel or don't use this fuel in an existing reactor. Okay? So this is going to be a tough sell to take existing licensed reactors and say I'm going to go through a licensing process and change to a more tolerant, accident-tolerant fuel, and that the owners are going to want to do this and be able to convince them of the benefit to be gained. Somebody had a question, sir.
You said it's been a long time that we've just accepted the use of zircon water. Do you think that if we were not in a time where we're kind of stagnant with the number of reactors, like if we were in a time of just building lots of reactors still, that we would be doing something like this?
It's interesting, you know, and obviously we're what-ifing history, and that's hard to do. But if we had a more rigorous and ambitious nuclear building program, but we built hundreds worldwide, right? And we didn't stop. We didn't stop and actually pursue this thought process any harder. We continued, and we built what, we're 400 and what, 450 or whatever the number is today, worldwide. At the point where we departed on this decision, we had only a handful of reactors comparatively. Sir?
Just as a follow-up to that, this whole idea that we started building stuff based on comparably little knowledge of things like zircaloy and other reactor components. We've built loads in the 70s, 60s, what have you. You know, there are been comparably few accidents based on, you see what point I'm getting at here, that we really didn't know that much when we started out. But now there's so much research into safety and like I said, choosing a new cladding and that kind of thing, and we're not willing to take that leap again. I'm just wondering whether there's a gap there.
Yeah, that potential, there is a gap.
But we don't want to take that jump forward.
Yeah,
So
and we're taking the jump in most of our minds here, and Paris said it in this morning, okay? He says I forget how he said it exactly, but basically we need to move on beyond light water reactor technology and go to other technologies. My reaction is there's nothing fundamentally wrong. It's not that I differ with Paris so much, because I think there's great advantages out of the advanced technologies. However, at the same time, I don't want to demonize light water reactor technology, because I think it's a very strong technology. We know a lot about it. I mean, that's a very important part. We know a lot about it. Sir?
With that comment in mind, I've actually, looking at, for example, the Chinese, they are building light water reactors that are basically just a slight improvement on a pretty old French derivative design, selling them as a CPR and selling them, not only building them in China, but selling them outside of China. And it seems to me that it's because they don't have, their licensing body is able to license something that is old technology, but in the US it wouldn't be able to license one of these existing old plants, even though they're still operationally much safer than any other form of power. Because that's one mentality, yes, we need to move forward technologically, but is there another mentality, maybe we should still be building old-fashioned reactors just because they're so cheap relative to an AP1000 relative to a liquid sodium cooled reactor?
And I think in part, and hardly a complete answer to your question, but in part it's a societal thing, okay? And in the US we have a very, I'm trying to think of the term, absolute protection thought process, the way we do our regulation. And we don't know how to deal yet with an acceptable risk reduction situation. We'll get into this a little bit in a while. With the absolute thought process, okay, I think in the US, we're going to continue to move towards newer designs like the current light water reactor generation, the so-called 3+ designs, with the passive characteristics, et cetera. And as we go to, we may build more of those, but we're also going to move if we're going to continue down the nuclear path, we're going to buy or design and build advanced technologies because of the safety case that can be demonstrated on these technologies. You're going to get a real mix, though. There are some folks that, and I won't put names on the companies here, there's some companies who value the safety side of this very strongly. There's other companies that do not. And you get a different answer. How strongly are we willing to pay for the improvements in the safety margin as we move to advanced technologies or different types of water reactor technology, different fuel forms, as an example, okay? I'm not giving you an answer because there isn't a good answer to this one, okay? And the risk tolerance is different in Russia, as an example. I'll take the extreme here, all right? Russia's risk tolerance is considerably higher than the US and most of the Western world, okay? It's true for the Chinese as well. But the Russians are probably more risk accepting than you'll ever see in the Western world.
Can I ask a follow-up question though? Is that a fundamental misunderstanding of not actually risk tolerance, but risk perception? Because it's actually like, if we're accepting building a coal plant in the United States, we're already accepting a higher level of risk than a nuclear reactor built in the States.
I agree. And so it is in part an educational and understanding process in perception of risk. Absolutely correct. People are generally are comfortable with other risks.
Right.
This risk on nuclear, as you all know very well, is kind of a demonized risk, and you work yourself out of the basement, if you will, in trying to bring them to an understanding of risk. I live over the hill from Pilgrim plant, okay, in Massachusetts, and my neighbors have a very difficult time with this discussion. Okay, because I said, look, I'm not about, they'll ask me, are you comfortable? You know, I said, of course I'm comfortable. This is technology I've grown up with. They said, well, why should we be comfortable? And I said, well, that's a very difficult answer unless you trust me and the conclusions I'm going to tell you. Okay, we can't get much further in this conversation because it requires a fair amount of knowledge of the technology. And it's not just nuclear. We could have the same conversation if it was a petrochemical plant, okay? Look at Bhopal in India, okay? I mean, we could have the same conversation, but it's an acceptance, and your point's well taken. It's an acceptance of risk tolerance, and it's a perception of risk, understanding of what the risk really is. And that's a challenge to all of us in this room. How do we tell that story as simply as we can and have people trust us? And we don't have that trust yet. We don't have that trust. Let's go on. Operating temperatures. The naval plants are 100 degrees cooler than commercial plants. That doesn't sound too exciting, except, as you know, that's an exponential relationship on temperature. Considerably different material behaviors at where a naval plant operates and where the experience was at the time. You remember, I'm giving you the thought process at the time. Back in the 60s and 70s, and where commercial units operate. And the naval plants weren't failure-free. They had problems. And those problems were well described into the commercial world. And companies like International Nickel in 1965 understood the susceptibilities of nickel-based alloys to pure water stress corrosion cracking. When did that become a discussion commercially? 15 years later. Okay? So how are the decisions made? This goes back to the management discussion, right? How are the decisions being made? How transparent is the discussion? How demanding is the management of the engineer, the scientist, principal investigator, of the level of knowledge that the individual has to have? So we don't end up, it's too easy to become an advocate of something. But are you a well-justified advocate for what you want to do? And that's where some of this occurs. Economics drove this discussion right here. This is an economic discussion.
Well, Phil, if you don't mind me interjecting as well.
Yeah. By the way, we won't have 100% agreement on some of this perspective.
No,
Okay?
I'm actually in agreement. a very interesting subject, not related to nickel alloys, but the stainless steel 304
Yep.
used BWRs. Why stainless steel 304 when General Electric and industry knew since World War II 304 stainless steel has stress corrosion cracking problems? Decision was made in the 50s and 60s. when PWR was competing with DWR in market share. And back then, you could build a nuclear plant for $160, $170 million. And it turns out that in a bid to some utilities, BWR was $500,000 more expensive than PWR. And PWR well, had different materials, but bottom line is to compete, the decision was made, and it's most engineers would do, is to go through the list of components of the plant and find out where it can save $500,000. And the difference between 316 stainless steel, which was the original design, and 304 stainless steel was,
That's right.
you had to guess,
I don't know the numbers, but I know the economics drove it, okay?
$500,000.
$500,000, okay? And
And that cost the industry hundreds of millions of dollars.
if I go forward on this, what he's just described is that. Here is the BWRs in the areas of susceptibility. All these little places that are shown here. This is where we got intergranular stress corrosion cracking in the stainless steel boiling water reactors as a result of decisions like you're describing. Okay? Did we do sufficient testing and qualification of the material before we applied it? The easy answer is no, by observation. But how did we make that decision and why were we confident at the time? That's a question you constantly have, rather than beat up GE here, okay, and the others. The issue is, how well did the management process, how well did the design process, how well did the technology development process ask the questions that need to be asked and make sure the basis was adequately solid? That sounds like a fairly academic discussion, but it's not. It's a reality that is constantly repeated in these discussions. Thank you for going through that. Because that's exactly what led us to that. And this is a similar discussion in the PWRs. We got primary stress corrosion cracking. Remember I said 1965. We knew, we had some pretty good inklings of what was going on here. And there's a lot of testing going on to understand it, but we continued to move forward and use these materials because one, they were available, and two, it was going to take time to go through the testing process. Not acceptable answers. And was driven by this 100-degree difference. Oops, going the wrong way. It was driven to a large extent by the 100-degree difference of where experience had been gained. We had some experience now. We've moved forward. We're 20 years down the road. Naval program operations. We've got experience, but it's in a certain environment, a certain capability. Okay? And we try to go too fast, too soon, commercially. You can see, he and I have both been in this argument before with the commercial world. I think it's obvious. It's how we pursue. Thermodynamic efficiency and economic benefit of higher achievable steam pressure. That drove it. Limited testing. Choice of austenitic stainlesses and nickel-based alloys, the points we just made. Material corrosion problems. This is important. Experienced during LWR plant operations have shown and continue to show today. Okay, there's some companies, one of which I'm on the board of directors for, that continues to make money on this right here. Because there continue to be the legacy of material problems, that some of which and many of which could have been understood better before we made the decision. I'm doing with hindsight. I'm Monday morning quarterbacking here, okay? But some of it could be foreseen. and some of it did exist, and some of the knowledge necessary to chase some of these things did exist. Thermont materials testing, corrosion behavior. Kerr touched on that. I'll emphasize it here. Reactivity control. Is this generally in the background of many of you, how we control reactivity? I just want to make sure that I don't get into something here that... basically, we've got, and I'm going to simplify this considerably. Basically, reactivity is a measure of whether or not I'm going to remain critical and whether I'm going to generate heat, okay, the way I want. Okay? Reactivity is just, it's currency. That's all it is. It's currency that measures how well I'm going to do that. I control it, and this is neutron inventory basically. I control it by the use of control rods, which are a poison material to neutrons. And in the PWR case, I use what's called a chemical shim, which is the use of boric acid, again, as a poison to neutron population in the reactor. Okay? Now, it's important here, and this is another departure. The Department of Energy reactors, like the Advanced Test Reactors, HIFER, and others, okay? The naval reactors and shipping port, none of them use boric acid for chemical shim. All right, they achieve long-term reactivity control, which is what you're dealing with here. I basically think of it as I deplete my ability for positive reactivity. That is my ability to be critical and generate heat. With time, I use it up, okay? And I want my reactivity, long-term reactivity control measure to be able to be depleted in a manner that follows that and allows me to stay critical and generate heat. Boric acid allows me to do that. I can also do it by what are called burnable poisons, okay, in the core. So why did we make this decision? Why did the commercial world decide it was going to use boric acid? Well, if it's just, the discussion was just, well, should we use boric acid or should we use burnable poison, other types of burnable poisons in the matrix of the fuel itself? That would be a relatively straightforward discussion. The discussion that's less straightforward is what are the knock-on effects of using boric acid? Boric acid is highly corrosive to carbon steels. And a truism is there is yet a reactor plant or any other plant, but I'll pick on reactors here, that doesn't leak. Equipment, it leaks. And the issue is, I may blow it out as steam through a safety valve, I may have it come out through the packing of a valve somewhere, but it leaks. And wherever I leak in the reactor coolant system in the PWR, I'm leaking boric acid as well. And if I'm in a continuous rewetting situation, wherever that boric acid lands, I'm corroding carbon steel. So if I go back and do the trade-off studies, okay, and I said, well, it's more expensive to tailor to what's called tailoring the core, putting burnable poisons in the core, to follow the reactivity characteristics. It is more expensive, no argument. If I build in then the cost of the operational cost here, of what this means to live with this particular design decision, operationally over a 60 or 80 year life, and deal with the downside consequences of the inspections and the material degradation, and some of the more exciting things like the Davis-Besse event with a big hole in the head, okay? Begin to say, did we do that right? Now, I don't, again, want to demonize the decisions that were made here on PWR use of boric acid for so-called chemical shim, okay? I want to demonize that. What I want to do is have you think, as you make decisions, it's how widely do you consider the knock-on effects? Does knock-on mean something to you here? How do I, the downstream effects of the decisions I make? Am I thinking through those decisions with a sufficient perspective on what it means to the operation of the plant over the long term. Am I doing my cost-benefit analysis, for instance, with all the right parameters? Do I include the information that's really important? Boric acid corrosion of carbon steel is nothing new. Okay, we knew that from day one. The question is, do we evaluate it practically in the commercial reactors?
Yeah, can I just add a comment on that? I think the other thing to bear in mind is that, of course, one thing that boron gives you is the ability to change your operations after you've started the core.
That's correct.
Whereas with thermal poisons, you have to make that decision at the design stage, and that's it, you're committed. So the global reactivity can be changed with boron. So once you're now operating a commercial reactor, unlike a Navy reactor, without going into details, obviously, the power needs that goes up and down in the commercial reactor allows you to make those changes with boron. If you try and do that, make those changes with control rods, which is what the BQRs do, or as importantly what the SMRs are now looking to do, the problem is now is that that global change in reactivity is by control blades or control rods, which now put greater demand on your fuel because of thermal cycling.
That's correct. I would never argue that control rods or control blades are the answer.
But in fact, that's exactly what the SMR, or some of the SMRs are doing.
Right.
And so that will and is introducing some impacts, particularly in the commercial world, where you may want to go up and down the load follow or other things. In a Navy reactor, of course, when you have method fuel, you can do that more readily. There's not so much further demand on the fuel, and they can cope with it versus an oxide fuel. So there's kind of a commercial driver. There was a good reason. The only reason to mention that is that there is that consideration was made for the AP1000 and AP600. They still decided to go with boron. Yet for the SMRs, they decided, in at least some of the cases, not to. So again, you consider this
Yeah, there's a plus column, and there's a negative column in this discussion, okay? And the message here, and thank you for your adding those thoughts to this, but the thought process is, are we adequately weighing all the considerations? Okay, you notice each one of these examples I'm using, they come back to the same thing, okay? Are we using something knowledgeably? Are we weighing the alternatives adequately? Okay, and in each of these examples, we didn't do that. So there's things to learn from here, and you can go into detail on many of these items. This is the dramatic picture you got to show, all right? This is the head on Davis-Besse, okay? What is this? This is in this area. I forget how thick this is, 10 inches? On that order. And all of this is gone. That's what you got in that previous slide. It's right down to the cladding that's on the inside of the carbon steel. You're down to 1/8 of an inch or so. And fortunately, Mother Nature allowed that little piece of cladding to be adequately pressure retentive, so we didn't have a blowout in LOCA in the process of the discussion. But here's a knock-on effect of a decision. And then, and I'll add now to what Per was discussing this morning with you on corrective action programs. If I take a look, and I won't go through this in detail with you, but if I go take a look at information that was available, and this is just one example. This is a management problem now, which exacerbated what they were experiencing. They had information over a period of years. This goes from 1996. Okay, over a period of years that was telling them that and I'll use airborne carbon as an example, airborne iron, but you can use any parameter you want here. Let me just choose one example to make the point very strongly. In a reactor like Davis-Besse, with a dry containment, I sample the air condition all the time. That's the instrumentation need. Okay, sample the air, make sure there isn't airborne activity beyond a certain amount, or trends in airborne activity beyond a certain amount, and that's what we're measuring here. Okay, it tells me that all's well. on the inside of containment. Now the device I do that with is this big hunk of instrumentation that's twice the size of that podium, okay? I suck air out of the containment and I have filters on it in addition to the monitoring stuff. And normally, operationally, I replace those filters every month. Not because I need to, because I do. Because I want to make sure that they're not clogging up in the interim period for some reason. They were replacing those filters every other day. And what was it due to? It was airborne iron. Okay? It was iron, not only activity, which is what this one's showing, but there's airborne iron in the containment. It's coming from somewhere, folks. All right? And you better understand what it is and where it's coming from. And this is where the failure of this corrective action program, and the time frames, this is activity in the containment, but the time frames are very revealing here about when you don't manage your corrective action program correctly, and how powerful it can be if you do manage it correctly, which was Farrah's point. The strength of the industry in general in managing it correctly, they just didn't manage it very well at all. And there were a lot of people. This wasn't one person. This is everybody that was involved. Tens of people were involved in this discussion alone, and the regulator. That's kind of interesting, isn't it? All right? And the regulator, like, you know, the guy that's supposed to be guarding the goal back here, okay, didn't do it either, okay? So it's a very, very sad story of how we got here. Unfortunately, it didn't end up.
Can I ask you a question?
Sure.
If possible? So, on the last side, what is this?
You just want to see the pen.
The 12?
What is, I'm sorry, what are you looking for?
Yeah, what happened right here? You know, this 12 thing? I'm sorry, can you see?
That's the 12th refueling outage.
Refuel.
They're
12
shut down.
refueling outage, okay.
That's true here, that's true here. Any place you go down, it turns out that's the refueling outage. Good question, but that's what, you know, when you expect it to do that, when you're shut down, okay? Questioning attitude. High performance standards, I won't build that up. Let's talk about safety. I've been talking about primarily operational indications and discussions here. This is safety now. Let's go a little more directly at the heart of these. Okay. Now, I picked up safety case definition. It's interesting. With the international mix that's in this room, we don't use this term in the United States, it turns out. I've used it for years, but most people in the U.S. don't use the word safety case. It's a European convention. I'm using a convention here which I think tells the story better, and it is a definition that I've typically seen in the European environment. But you go through these things, okay? Here's how I go put the safety case together. A compelling and comprehensive justification that the risks and hazards have been assessed, limits and conditions put in place. I can tell a story. Exceptionally important, fundamental aspect of the way we do nuclear work. Okay? The safety case for reactors. And the things involved in that are the bullets. And I'll let you read them. I won't read them to you. Now, the primary hazard, obviously, in our business is radioactive fission products. That's our primary image. And we have all kinds of automated actions in light water reactors to preclude core damage. We have multiple barriers, although one of those barriers is questionable at some times, as we discussed earlier, the metallic barrier. Now, both TMI-2 and Fukushima were obviously the failure of that barrier because of a failure to remove decay heat. It is, and I realize the mix of people's background here. Does decay heat mean something to everybody in this room? All right, I'll let us go on. Now this is a kind of a digression, but I just mentioned this. The industry was at this time, commercially, driving along on the basis of some worst case accidents. And what did change at that time was an understanding that what we consider the worst case accidents weren't. from a LOCA standpoint. We didn't have the appreciation of what's called an intersystem LOCA. Okay, we didn't have a full understanding of our accident basis, where there are actually worse conditions that can be achieved than the bounding accidents that we had had. So I just want to put that in here as a way of background. It's a change. Key message in here. All licensed reactors have been subject to the scrutiny of industry and the regulatory design review and acceptance process. We put them through the ringer. Okay? There are prescriptive requirements and regulation, but they're not sufficient. We've managed to find a bunch of examples where they weren't. And in all of these accidents and major events, I want you to think about this if you would. In all of the accidents and major events that have occurred that we've either touched upon or will, the conditions achieved are well beyond the licensing design basis for the plant. Otherwise, we took the plants to conditions that we did not ever anticipate. It wasn't like they failed because they were designed incorrectly. We didn't anticipate the conditions they could find themselves in. And in particular, TMI-2, Chernobyl, Fukushima, Davis-Besse, Browns Ferry, every one of those, irrespective of whether it was core damage in a couple of those cases, we took the plants well beyond design basis. So our thought process as designers had something to be desired, right? Think about that. We weren't fully knowledgeable of what was important. I can't stress this enough. We've learned, here's the lessons learned took us down this page. Why couldn't we anticipate it? It's a question I ask myself. Why didn't we anticipate some of these things? Well, a couple of them we could. We're going to talk about a couple of them. It's just to play with that thought for a moment. And I'm just going to use, I want to define a term here, which is not well defined, which is called defense in depth. In the United States, and I don't know about Europe, you're going to have to help me on this one, there is no real definition of this concept. There's a philosophy that basically layers things in place. You know, this layer fails, this layer will pick it up. Okay, that whole thought process is defense in depth. But it's not well codified in the U.S. Is it? How is it in Europe? All right, not either. And we depend on it. Okay, we depend on this as a fundamental aspect of how we design and regulate our reactors. So let's talk about this for a minute. There's a particular area which I want to talk about, which is a thing called common cause or common mode failures. And I don't know if that terminology is, let me I'm hitting the wrong button, that's why I'm not getting what I want. Let's talk about single failure resilience. Now, this is fundamental in the nuclear world, in the United States in particular, and I don't know regulations in other countries that well. But this is basically the thing, if something fails, is that the end of the day? The answer is no. I'm able to handle certain numbers of an active failure, passive failure, certain configurations. It's well stylized, and my resilience to a piece of equipment failing that I originally intended to be there for safety purposes. And then I layer below that defense in depth, where it may be even worse than what I anticipated. This is interesting. These are the safety valves. This is Limerick Unit 1, boiling water reactor. 12 of the 14 safety relief valves fail to lift within prescribed requirements. I need at least half of these to work right to provide overpressure protection in this reactor. Okay? What happened? We had a common mode or common cause, and I'll differentiate between them as we go here. All of them will operate open to pressures above that required to protect the system. The problem had to do with corrosion behavior, happened to be in a pilot seat and disc, but we won't go into the detail here. The issue is there was a corrosion mechanism, design-related material selection failure, that took single failure resilience and just kicked it out the door. Okay, we weren't ready for common mode in this case, design, common mode failure. We didn't anticipate it. And where would we have gone if it had actually been required to do what it's supposed to do? Okay, this is testing, so we didn't threaten anybody. But in testing, we found it didn't work. Let me take one that's more complex. This is our friend David Spessy again. Okay? This is 1985. And the reason I happen to know a great deal about this, I was part of the management team that was brought in to recover this plant after it went through all this. Okay? And so this kind of became personal after a while. What we found and how we rectified it and fixed it. And one of the central aspects of it was common cause failures. We found things that failed, their ability to handle single failures went right out the door. They couldn't handle the multiple failures that occurred. Common cause. For instance, the operator, the way this got set up, and I'll just walk it through you so you have a fundamental understanding of it. And by the way, is this particular event taught very often? Is it?
This is the first one.
Was that right?
Yes.
You say it is taught?
Yeah, okay, you're saying it's David Spessy taught in classes?
Yes.
Not in most undergraduate classes. I took a systems, so maybe some system classes or theory classes.
Okay, it's important to teach this just because what we learned here. We didn't wreck the core, fortunately. Okay, it was lucky, and it was lucky. And I'll just, as I set this up, I'll walk through why it was lucky. This is serendipity.
And it just said in the UK, this is standard.
Good.
It's still another.
Good. I haven't found it very much in the U.S. That's why I'm glad to hear that. Okay.
It's mostly about Fukushima, Chernobyl, at least for.
So it goes to the more accident, where we really did damage the core. In this case, an operator made a mistake, and it had to do with a human factors problem. We set them up for the problem, and the designer, we set them up for it, okay? And the operator reached in, trying to do his job, and he makes a mistake. And his mistake precipitated a particular safety system acting and just like it was designed, and it put us in a very unusual position, immediately outside of our design basis. All right, just so one common cause right there. Secondly, we had auxiliary feed water pump turbines. Now these are steam-driven pumps that basically drive water into the steam generators to cool the reactor. They both tripped. This is redundancy. They were redundant for single failure purposes, right? They both tripped. They both tripped for the same reason. And we'll go on to that in just a few minutes. Okay? And then as a result of the first thing, the operator got his fingers in it incorrectly. Okay? Two motor operated valves in the redundant discharge flow paths for the auxiliary feed water pumps shut and wouldn't open. Now, the philosophy here, and there's several layers of philosophy in this discussion which are important. One is, and Claire said it this morning, keep things simple. This is an exceptionally complex safety system. You really have to be clever to figure out how it might fail. And we hadn't adequately figured out how it might fail. It was licensed, it was reviewed, all the stuff, but we hadn't figured out how it could fail. In this case, the philosophy of this particular system, which was a core philosophy, was basically if you think, it's called the steam and feed water rupture control system, if you think there's a break somewhere in the feed water or steam systems, isolate everything. All decay heat removal basically removed from the plant. And the philosophy was, if I do that, and now I sit back and figure out based on my plant indications where I am, I go open up the right valves and go do the right things and get my decay heat restored. Okay? Well, one of the things I depended on is these two motor operated valves to come back open when I wanted them to come back open. Because that's the flow path and those pumps that just oversped, okay, and weren't running anyway. Okay? Well, they wouldn't go open. Where did this lead us? This led us to the motor operated valve program worldwide, right here. Because what we had is a common cause failure. The way we were maintaining, setting up, and testing those motor operated valves, which was common across the industry worldwide, was wrong. We had a common cause failure that was so far beyond any single failure resilience thought process. Okay? We got multiple common cause failures. Now, why do I spend the time on this? If I come to the current day and I say, okay, if I go to the general design criteria, the US regulations, and I said, have we fixed our understanding of this? The answer is no. We basically do it one at a time. We take a look at the particular plant configuration, and there is basically a one-of-a-kind analysis done of the level of susceptibility to common cause failures. There's no codification, there's no standard to it. So as designers, okay, I presume your world's going to be based on risk-informed environment. I hope it is, okay? And the risk-informed environment presumably will help us through this discussion by helping to identify the vulnerabilities. Because the prescriptive requirement, the way it is in US regulation, and it's really, I believe it's not that much different in the European requirement, okay? We relied initially in the industry on redundancy to solve our resilience problems, and we basically dismissed diversity. And when we dismiss diversity, where it's not to solve, it doesn't solve all mankind's problems, okay? So common cause, common maintenance, common design, common operational problems, and they come striking right through, and it happened to be demonstrated all at once in this particular plant. Oh, by the way, talk about simplicity. You know, Per made the point this morning. It happens to be a boiling water reactor, what's called a RIXI pump. But it's the same pump, basically, as the auxiliary feed water pumps that were in Davis-Bessey. And I got a steam turbine, and I got a pump end on this, and I got a control system, I got governors, and et cetera. Does that look like a simple piece of machinery to keep operating? Okay? And I require this piece of machinery to fire when I tell it to fire. All right? And put water into the steam generators and protect the plant. But I've got this little steam plant of its own design right here, okay? Which misoperated, oversped, and resulted in losing all sorts of water to the plant. Now, I'm going to add serendipity in here, because this is kind of a homespun tale, but I'm going to add something in here that was kind of interesting during this event. The operators recognized the plant's temperatures are going up. Core temperatures are climbing. Indicated water inventory of the steam generators disappeared. Okay, there's really still water there, but indicated we had disappeared. Okay, they're trying to figure out how we deal with this, and so they're dispatching operators. Now, this is a time where the operators may have contributed to the problem, but they're also now going to pull our rear ends out of the fire. Okay, and so they're running around trying to figure out, how do I get these valves back open? How to get these pumps running? How do I get water to the reactor? They know the essentials. How do I get to a position where decay heat removal is part of what's going on here? I have none going on right now. No decay heat removal off that reactor. Temperature's climbing. You remember in the background I mentioned that there was a management decision not to go to feed and lead. Remember that? Over here. So my backup, my defense in depth, was being ignored. So I'm running around. Now, in Davis-Bessey, like many plants, in Davis-Bessey in the turbine building, which is where these things are in the basement, two of these are in the basement of the turbine building. In a locked area, security in total. Historically, we've relied on redundancy, separation, and independence. You recognize those terms. However, those do not remove the potential for common mode. Diversity helps, but doesn't solve it. And you shouldn't depend on defense in depth as the way out of this. This right here is an interesting slide for you to think about later. How do I deal with this in design of new plants? Now this one has to do with, do I understand what physical phenomena are going on? Now, this is a plant in Germany, Bergassen. I don't know if it even operates anymore, but an old boiling water reactor.
No, I'm just pretty sure it's not the GE BW but
I'm sorry?
I'm pretty sure it's not the GE.
Oh, no, it's not the GE, no,
It's
yeah,
the
thank
German
you.
building,
Yeah, no. And I'm told, I don't know, I'm told this is what Bergassen looked like. I don't know if it is or not, okay? All right, it had a torus. Let's accept that who gave this to me is right, and it has a torus, okay? Now what happened? Well, the way the BWR works, okay, amongst other things, is the safety relief valves open on high pressure transients. And also in the case of a loco, they depressurize the primary system. That's the basic fundamental approach. I depressurize the primary system rather than leaving it at high pressure, which is the PWR approach to the line. So I got two things. Now I got this line. Let me go back one more. I've got a line that goes from up in the upper areas here into this torus. So I dump this energy into the water pool, the suppression pool that's in this torus. That's the concept. Well, the line is full of air, and if it's an inerted containment, it's full of nitrogen. Okay, so first thing I got to do is I got to get the air out of there. I open it up and I dump the steam into that line. Okay? And also now I have all this steam that's coming out of the system, you know, and it's all dumping into this torus. Now, that sounds kind of exciting, you know, after the fact. We didn't consider it very exciting when this was designed. Bergassen showed us that we didn't understand these phenomena very well. It's a very rough, you know, I dump air into the, huge amounts of air into the torus water, and then all this steam with rough condensation as it hits that water. And it basically mechanically damaged that torus in that particular plant. This is in the 70s, 72. Now, I won't run you through all the pieces of this. Okay? I won't run you through all the pieces of it, but what it demonstrates, if you go through this, and it was a wake-up call for the industry worldwide, because all the GE plants have the same basic concept, okay? Is we hadn't taken some fundamental understanding of phenomena, or say it differently, we had not understood how little we understood of some basic physical phenomena and based it as to how we were going to approach the safety case for this reactor. Now you say, well, how could we have been that ignorant? Well, it's a question of asking yourself the question of how fast do we want to deliver these machines commercially? How important did we think that is? How much did we believe in the modeling capability that we had at the time, which was fairly limited, okay? I did some analyses in the late 70s to go to the how do you fix this problem on US BWRs. And the analytical tools, I was using a timeshare machine, that concept probably doesn't even exist today. Using a timeshare machine with card decks, there was better the length of this table. Okay. We didn't have the electronic files. We ran the analyses, and we had to combine programs to go to this analysis. GE and its counterpart in Europe had never really gone through a full analysis of what happens when I dump air, I dump steam, I condense it in this water, and what do I need to do about that? There's a fix to this. You know, you basically do what's called a T-quencher on the end of it. You distribute the energy. Okay, you can fix it. The question is, why didn't you think about it initially? That's where you want to ask yourself as designers, have you just stepped straight through an assumption without adequately questioning your design process and your design thought process? This is a clear example of that problem. This took 5 years to correct industry-wide. Hundreds of millions of dollars of corrective actions. Backfitted into plants which were already now contaminated, radioactively contaminated. Very expensive oversight. Okay? Not the only one. This is an example, but it was the example of a design decision which wasn't adequately thought through. Now, you guys know this one, right? Fukushima. What's your thought process on design decisions in Fukushima that actually resulted in the major part of it? I'm not even gonna, I wanna make sure you guys, you have the background. What do you think are the important failures in the design thought process that went into that BWR? It's the basic same BWR that we just looked at, that same torus design. In this case, and some of the answers are up there, the answer is, why did we make such a decision to put the essential power in the basement? That was one bad decision. Not to consider the tsunami, which we knew about. We knew about it historically. This is not a surprise to the Japanese. Why did we do this? What's your thought process, and how do you think, what failed in the design thought process? Anybody? Sir?
They didn't plan for that. They built the wall 8 meters rather than 10.
I'm sorry, I can't quite hear you.
They built the wall, the tsunami defense wall, 8 meters rather than 10 because they didn't expect, once in however many years they planned for. They only planned for a more likely tsunami.
It was 1 in 1,000 years versus what actually happened with a 1 in 10,000 year event. So I personally think it's slightly unfair to say they didn't think about it, because I mean.
That's okay, go ahead.
Ground, which also doesn't help against tsunamis, and that's why like the 5th and 6th units were really not threatened by the tsunami because they're way above. And at that time they thought that being closer to the rock would help the plant be more resistant to earthquakes. So.
Has any of you read the, I don't remember what it's called specifically, but the post-accident report that was done on this? It's extremely interesting and very eye-opening in the Japanese culture. They have a very difficult time with the questioning attitude that we try to develop worldwide. Okay? They have a difficult time with that, and it has to do with their respect for senior people. Now, I like that in older folks. I would like some of that respect occasionally, but the issue is it caused a problem in this design process. Okay? There was insufficient questioning on decisions such as you talked about. How high do I build the wall? Am I designing for one in how many thousands of years? Or am I designing for 1 in every 10,000 or 100,000 years? What am I going to design for? How big's the wall? Why did I put it in the basement? I didn't have to put it in the basement. Power supply. U.S. plants in general, I don't know of any that are in the basement. There may be one, I just don't know about it. But they tend to be above grade. Okay? And one of the reasons is I don't want to try to deal with flooding events, not tsunamis. Typically, that hasn't been in our thought process. But the issue is I don't want to deal with flooding. So I build it above grade. And any challenge that may come from rivers overflowing and that type of thing. All right? We've got weaknesses. We're not perfect in this regard. But the decision to put an essential power supply in the basement, when you got a plant full of water and you're sitting next to the ocean, it's a question that you ask yourself, how do we make it? Now, again, let's not criticize the Japanese here. That's not the issue. Okay? The issue is, as you go forward in your experience and in your careers, how do you ensure that there is a transparent and candid and well-managed process by which design decisions are made? Because it's essential to your success as designers in advanced reactor technologies and innovation of any sort. Let me go to slide 60 now. Let's talk about this a little bit. By the way, do we work breaks formally into this thing, or is just everybody goes when they need to?
This runs till 4:30.
Yeah, I just want to make sure folks didn't.
Yeah.
I'm the old guy in the room, so I go more often. Look at these items. Now, the first item, designer must anticipate events in the operating conditions, all those words. Okay, all that's true. That's nice. But here are design targets. Intrinsic safety. Should that be the cornerstone of the design? And I define what I mean by intrinsic safety here. No motive power, no fluid required. Is that an objective we ought to use? How would that apply to a molten salt reactor? How does it apply to a gas reactor? How does it apply to a lead-cooled reactor? Is it the right objective? I'm not suggesting these have to be your list. This is my list. Okay? But intrinsic safety says, how do I ensure that I minimize the possibility to eliminate my capability to remove decay heat? How do I make that so it's vanishingly unlikely that I will lose decay heat removal capability in a plant? Now, I told you earlier, I'm a proponent of gas-cooled reactors. It plays this game. It goes through this intrinsic safety game. It doesn't need any fluid. It doesn't need the helium. It does not require any motive power. That was built into the thought process by the Germans and General Atomics originally, okay, as to how you approach gas-cooled reactors. As we approach these other reactors, should that be there, or is passive safety enough? And that's the argument you got to. When I use passive safety, I use the like the AP1000, where I have a high confidence that the water cooling of the reactor will occur, okay, upon an accident occurring. Is that enough? Why is passive enough, or is intrinsic safety enough? Simplicity we've already talked about. Impervious to direct and consequential effects of external events. Okay? Intentionally be able to basically say it doesn't matter what happens outside. Okay? I'm self-contained and I survive. The next one is operation of the operator action rather is not required to mitigate an accident. And operator actions cannot cause or worsen an accident. We went through some examples here of both sides of that, where the operators have to involve themselves in water reactor technology at some point to keep the core cool. On the other hand, they could go in and cause mischief as well. Unintentional, but they can cause mischief to occur. And it can also save our bacon, okay? And they do all of those. But what you'd like is, I don't need an operator. Now, that doesn't mean I make it an autonomous operation, because I'm going to not think of everything. And I want the operator there to respond when I haven't thought of it. But I don't want to have to depend on him, nor make it something where it's vulnerable to his or her operation. Okay? The next one is, gee, we really don't need emergency planning. That's what that one translates to. No off-site public safety, environmental, and economic consequences for severe accidents. Water reactors can't fulfill this at all. But can we design reactors that can do so? Again, a gas reactor gets closer to this. Okay? It doesn't eliminate this, but it gets closer to this. Keep the primary and secondary sides functionally separate. This gets in part to, it's both a regulatory consideration and a practical business consideration if we're going to cogenerate. I want the ability to separate my plant from the petrochemical plant as an example, so the reactor doesn't see the effects, okay, of that plant. And there are provisions for severe accident backup cooling and containment control if that's necessary. If I haven't already eliminated that as a detail. And I got a tool down here as a systematic risk analysis. So give me your reaction. Does this answer the mail? Is it asking too much? Is it asking not enough? What are your reactions to these? Because this is where I would like to leave some of the conversation today and take some other questions if there are any, okay? But I'd like to have a thought process on this. Should this be the objective for our advanced reactor technologies? What are your reactions to these?
Well, just a general comment, I thought it was a really interesting point you made that the designer should aim to have the operator role to respond to things that the designer doesn't think of, rather than be an integral part of plant operation. I think that's an interesting reevaluation of that role, and certainly has interesting knock-on effects to the way that management would have to approach operating a plant.
That's correct.
And training of operators in what they do. Certainly, they would have a good bit more breadth of knowledge probably, and maybe less, well, certainly different responsibilities.
And let me build on your point. I think it's very, very astute observation. The gentleman who happens to be the pre-operations director at Hinkley Point C today, okay? He's an operator who I've worked a great deal with in U.S. plants. He has the ability to do what you just talked about because he is able to separate himself back, and his knowledge is very deep in terms of the plant design. By the way, he's the guy in the larger version of this discussion, which goes on for 3 days, who talks about some of that design philosophy and how the operator approaches it. Okay? But it's an extremely important concept. Whether it's achievable, okay, is a question. I think it is, but it's one that you ought to think seriously about, okay? Because of foibles of being human, okay? It's the fact we are, and we make mistakes. When the engineering and the scientific community make, this is an argument now goes on in operating plants. When the engineering and scientific community make mistakes, it's usually on paper. Okay? When the operator makes a mistake, it can have catastrophic effects. Okay? So his world is a different world. His and her world are an entirely different world here. Okay? And we have to help them to minimize the demand on coming up with the right answer. Hopefully eliminate it as a regular course, or, and I'll do an and, which you just observed, which was have them there for the things that we have somehow managed in our best efforts to overlook, okay? And have them have that capability that you described well, which I'll say repeat because I want to make sure everybody heard it, because I think your point's well taken. They have to have a knowledge of the plant, which is different than operators typically have today. An understanding of the design and response of the plant and what can be done to rectify issues. Okay, so it's a different, so you have a design challenge and you have an operator education challenge that occurs here. Other observations, please.
I'd just like to build on that because I know digitization or digital, I think that the challenge and is that digitalization. I think that for like existing plants, that the move would be to work with operators to figure out how you can have the least change in designing a new system, or not the least change, but the easiest transition in terms of training and education. If that's such an important point, how do how would you tackle that problem?
You asked a very interesting set of questions here, and there's several pieces to this that I'll suggest we talk about. Let me take your last point first, the transition. At our favorite plant, Davis Bessey, okay, in the late 80s, we had a bunch of, as we had recovered the plant, brought it back, and it was operating, and now we were going through the next refueling cycle. And we said this control room is full of obsolescent equipment. Now this happens to be indicating equipment, but it's the same issue at the end of the day. And we have all these strip chart recorders and all this business, okay? We need to get rid of this. And the indications are all analog indications. And the operator, how does he know whether the analog indicator is working right? You know, it goes over and taps it, right? That's real, that's solid, okay? Now, and so went to digital indications. And found that it was interesting to manage that change. The operators were very uncomfortable with it, okay? Because now they could previously just kind of examine the board, control board I'm talking about now, and everything was kind of where it belonged. Now they had to read the indication, human factors, had to read it. They could no longer just use this pass by, where's the needle? Where are things? Much more reliable, but less comfortable to the operator. Now let me go to your next, and it was a fair management effort to retrain them as to how they monitored the control boards and were sensitive to plant changes. Very, very excellent question. Second part of it on digital controls in general. Okay, now we've had a fight in the United States. I don't know how it's gone in Europe. Okay, on how we regulate digital controls. And if I go through I won't drag you through the whole thing, but basically what it comes down to, in my understanding, is we've decided diversity is the answer. Okay, we're going to avoid common mode failures in the digital systems by a method of applying diversity. Okay, the specifics of how we do that vary greatly, but that's the basic thought. Now the operating plants in that context, okay, say, now wait a minute, guys. The systems I'm already have licensed, and this reactor that's licensed out here isn't common cause proof anyway. It's single failure resilient, but it is not common cause or common mode resilient. So you've now just asked me to spend a lot of money on diverse, solid state digital controls to achieve this diversity, and I haven't changed the risk profile on the rest of the plant. So part of the resistance that you see in the United States, and I don't know how it's played in Europe, I haven't paid attention to that, okay? The resistance you see in the United States to this in the operating plants is the sheer economics of why do I have to take such huge leaps for digital controls when I am not doing nothing to fix the vulnerability of the rest of the plant to common cause, an existing license. Now, as I go to a new plant, like you know, the AP1000s and this kind of thing, I address it because it's integral to the discussion. But as I try to backfit it into existing licensed reactors, part of the argument, and it's unresolved at this present time. I had this debate went on about a year ago with some former commissioners and chairman of our NRC in a fairly candid conversation. And I'll mention one name in there. Some of you may know George Apostolakis, okay, at MIT. Okay? And George is Mr. Risk. Okay? And George has a particular perspective. And George's perspective is fine, except when it runs right straight up against what we just described. What are we doing because we haven't improved the common cause or common mode failure vulnerability of these existing licensed plants we do this. So if I come back to part of your question, which is, will we see movement on this? I don't know the answer. Right now, the requirements as they're implemented are primarily focused on how you would answer the question for a new design plant. I think we need to look for another way out of this. Some form, this would be an interesting challenge to you guys. I don't know if it's on your project list or not. Okay? An interesting challenge of how would you approach a risk-informed discussion on digital control backfit into an existing licensed plant. How would you risk-inform that? The other thing we don't have in our regulatory scheme today is an agreed-to risk-informed process. So we got two problems. How do we backfit it into existing licensed plants? How do we, given that we're going to try to do it, how do we deal with the dichotomy and the contradiction that exists between what we're trying to do with digital controls and what the plants are currently licensed and designed and implemented to do? Sir?
You may actually have three risks.
Okay,
Three
good.
problems.
More than I recognized.
Yeah, and the third problem has to do with quality assurance for the software. You're stating that not only for digital control systems, but to fully automatic control rooms. One of the major problems with the NRC is being able to do quality assurance on the software. The software may run tens, hundreds of thousands of lines of software. To make sure that the input, the output is equal to the output that you expect from the program. You don't have a number of problems like common cause failures in the software, quality assurance in terms of the maintenance of the QA of the software itself. Major problems that the industry has been working on with NRC for how many years?
20 years.
20 years.
And it's not the NRC versus the industry at all. This is, we haven't been able to, as an industry, to bring a sufficient case to our regulator. That's the way I look at life, okay? We need to bring a sufficient case to the regulator that convinces the regulator that there's a different way to solve this problem. That's why I think it's an interesting project, either within this workshop, but I think it's bigger than that. It's something that somebody ought to go after. Sir?
So does the NRC mandate or regulate the control parameters of a reactor? Let's say you have a YouTube steam generator reactor and you have these directly controlled parameters. Is that mandated by the NRC or is that something designed by their?
Let me do it in simplest terms. It's approved by the NRC, if you will, as part of your license. Otherwise, the designer or designers establish those parameters.
So there's room for innovation in that.
Yes, sir. Okay?
The NRC.
Now, the answer is yes. Now let's be real for a moment. Okay? Anytime we talk about innovation, it's a change. And what do people dislike? Change. Okay, that's just built into our most people's innate nature. Okay? And so in this case, we're changing approach. Let me build on your point, because I think it's a very interesting point. The next generation nuclear plant, a high temperature gas reactor, we engaged with NRC as led by the Idaho National Laboratory, but with great amounts of industry involved, into the what's called a pre-application process. That is, we're not applying for a license yet. We're in the discussions of how do we establish the technical requirements and policy requirements that will apply now to an advanced reactor. And we were using the high temperature gas reactor as a surrogate for any advanced reactor. Now that's not being a perfect surrogate, but you're trying to do that. So it's technology inclusive, if you will. It won't be technology neutral. We're not smart enough for that. Okay. In doing so, we introduced new concepts such as a classical containment. Let me take to your point. Not a parameter in this case, but a physical barrier. A classical containment isn't required for a gas-cooled reactor. That's our argument, okay? Because the containment is at the fuel level. Okay, the fuel is your container, if you will, all right? Now, it's a more involved argument, but I'll just leave it at that simple level for a second. Taking the fundamental concept, it's kind of like moving a parameter around for innovation, okay? Taking a fundamental concept of a canned containment and moving that over here to what gets labeled as a functional containment, that's the term they use, which says the fuel now is your containment, is a large discussion. Now, it takes education, it takes acceptance on the part of the management within NRC to accept a change to the way they're doing business, because they are they understand water reactor technologies very well. As you introduce new technologies and changes of this sort, you find the natural human resistance to change, okay? And whereas, so regulation allows it. There's nothing that stops it. But, except for the human nature of how do you get through it and do you have sufficient basis? Now, in order to have the argument that I just offered to you on containment in the fuel versus containment as a building, okay, requires an understanding of how we qualified production fuel, the TRISO fuel, how we qualified that, to believe that what I just said is correct. Now, all the things that go on in doing so. and a gentleman named Dave Petty at INL, okay, and his counterparts at Oak Ridge have spent the last 14 years now, going through this, and they got another few years to go, okay? Of getting to the point of taking where they are today is high confidence, but taking it to the total proof that we convince ourselves, first of all, that this change of concept, the equivalent of a parameter change, okay? This change of concept is correct, and then getting the regulator to agree with it. So the process is not simple, the opening is there, and as we develop more and more of these openings in the tech advanced reactors with the regulator, it's a very important discussion. Now, the regulating schemes in other countries are somewhat different. And each are, and I won't try to generalize here, each are a little different how they approach these things. The US regulatory requirements are highly prescriptive, not to the parameter level, but they're highly prescriptive, okay? So we have a larger burden, and so as we bring in, for instance, risk-informed thought processes. There's a gentleman who some of you, I think, know from our conversation last night, a fellow named Amir Afzali with Southern Company, who's leading an effort right now, okay, to put together the story of how do we take where we started with the next generation nuclear plant and now continue pre-application activity for the changes that are necessary to get to a technology or a technical and policy framework that will support advanced reactors, and if we're clever enough, that will include most of what's here. Now, I know there's one exception right now, all right, it's just as we sit here, okay? And I forget who it was at lunch that mentioned it to me. A liquid core, molten core, okay? It's not in our thought process today, okay? It's a core that's in the pot, if you will, in the vessel, is the basis upon which we have thought about this. Molten core brings a new set of thought processes in it. Southern Company is also working on that concept with Oak Ridge and TerraPower and others. So it'll be very interesting to see how that evolves and how that influences this discussion with the regulator at the right point, with technology inclusive advanced reactor license. Other questions? Sir?
So just got a point on this. Also the other kind of looking forward to advanced reactors has always involved some kind of comparison to Gen 3, and generally they say must be safer than Gen 3. I think that's essential.
Well, rather than I answer your question, let me open it to the floor. What do folks think? We have to be safer. I'm not sure I know exactly what that means yet, but let's define it as well. Safer than Gen 3. What's your thoughts?
I mean, if we're to get any kind of like political weight in approving of something greater than that, it would have to be. Is my opinion.
Other thoughts?
You can always make something safe, but it always comes at a cost.
Important consideration. The economics are in here, okay? But does that mean that we don't do it? I mean, I can flip that around on its head. Is it an important objective? If I wrote that up, we'll add it up there just for our discussion, okay? Safer than Gen 3, okay?
I would hope that it doesn't always have to come at a cost, because it would force you to look for ways that you don't compromise on the economics while in safety, which, I mean, some reactor designs reap some benefits, not when those benefits are not their original goal. So just like my bias or whatever, I work with molten salt, and there are some aspects of the fluoride salt high temperature reactor that are passive safety, which, I mean, when you remove the need for other systems, you remove some costs. Maybe the entire design, it's hard to make a case that's more economical than something that's fully fledged and already exists, but you may end up saving in the future. So I feel like, well, from my perspective, it is frustrating if like you start out by building a nuclear reactor, right? You're not building a safe machine. So the fact that the first thing you want to start with is safety seems kind of silly, but hopefully in designing for safety, you
Excuse me, I'm sorry, I didn't, whoever wants to go next there, yeah.
Well, so I'd say, speaking about Amir's program with Southern, when you look at what PRA is at level 1, 2, and 3, it ultimately comes down to radioactive release to the public. That's level 3. You say, what is your initiating event that can lead to that? And if you design around preventing this level 3, the right side, which is actually affecting the public on that end, and look at what you're actually most likely to have a release from, it can determine how important your initiating events are. And so you can use that same approach for any reactor design. It just matters how you're defining radioactive release. Like if it's a molten salt, you don't have the same issues of a pressurized water reactor where you have a gas cloud. So it's always keep in mind your end results of what you're trying to avoid on one end, not necessarily. But also, I mean, obviously, think about your initiative, but that's how you kind of work towards overall being a safer and cheaper design to prioritize.
So let me ask you a question. What does safer mean? We're having a hard time with this discussion. What's safer mean? What's the parameter in your mind? And you asked the question to start with, so I'm going to give it back to you. What does safer seem to mean to you in this case?
Yeah, I think that's an important feature. So risk to humans, the risk to the environment, avoiding the plant to but there's also, safe in the respect of the kind of risks that exist, like economic risks and risks of downtime, loss of performance. Safety is huge.
Okay.
This would be a really good discussion to have with the representative from Innovates.
Right.
Remember what they is. People have safety goals, they have quantitative safety goals. And they will have a history over the years of some improvements. They have a 3-year goal, 5-year goal. So that would be a really good question to ask him.
That's smart, right?
And let's carry that question forward, just as you're suggesting. The second part of this, our NRC has established a set of protective action guidelines. Actually, they're EPA guidelines. Okay? And they establish what is acceptable, and it's, I don't think of them in these terms, but it has to do with the risk to health of individuals. I mean, the EPA thing's developed in that manner. Okay? And that then is translated into parameters that we can use in the design world. And those protective action guidelines are the fundamental aspect that we have to fulfill. Now, the thing that's interesting is every light water reactor that's licensed in the United States already fulfills it. So the question is, what are we working on? Well, we're working on margin. We're working on, right now, I'm going to give an opinion, and I'm interested if you guys agree. What we're working on is how do we achieve it? I can get and fulfill the protective action guidelines and not have intrinsic safety. I go to intrinsic safety because the benefits it gives me, and it reduces the risk of something else occurring, well, like Fukushima. Fukushima needed water. Fukushima needed power. That water reactor needed those things, and it couldn't fulfill, but it was a licensed reactor, and very similar to the licensed reactors in the United States. Differences in specifics, but very similar. The licensed reactors in the United States fulfill the translation of those EPA guidelines. Okay? Now, so we're talking about how we achieve it in primary fact. I mean, that's in reality what you see a lot of up here, is how do you achieve those with what level of assurity? Of surety, I guess is English, of surety, okay? With what level of confidence do I achieve that safety case? If I have intrinsic safety, I'm way up high on the scale. I need nothing, it sits there and cooks, and it doesn't care whether it's cooled other than by radiation, and in a gas-cooled reactor case, by radiation and conduction of the walls, and then radiation to the rest of the world. And that's how it cools itself. With molten salt reactor, I have to have a fluid, right? So okay, so it's a little notch down, and then you argue whether it's adequate or not adequate. Okay? The operator action is I can do that with, I can do it with active systems and fulfill, because I do, in licensed reactors, fulfill those guidelines. So it's, how do I achieve it? Now, there's no precise answer to your question because nobody has defined it. There's lots of philosophy out there on how you might do it. And that's what this discussion is. It's how would you approach it to give yourselves the highest confidence? Maybe there's more items that belong up there or a different way of explaining it. But how would you approach it to give yourself the highest confidence that you can see as a new reactor designer that you will achieve fulfillment of those protective action guidelines? If those are the right guidelines. I keep going back to those because that's what the standard is in the United States today.
So in the UK, we have to do, we have to do some kind of probabilistic design assessment on some level. And we had someone come in from Hitachi and show, and they were able to put up an AP1000 and a bunch of other reactors, and then you bought them water reactor, and they were able to show a figure that showed that we've done our testing, we've had them verified, and it's lower than these other reactors. And it was, what the guy said, yes, I can't remember who it was who said this, but to go to their board and say we're going to get a reactor, but it's not the safest on the market, that's difficult. So, if you're a market force, you have to design the safest reactors on the market.
Well, I look at your point, and let me go to the practical aspect of what you're talking about. Reactor comparisons are futile, because we haven't found so far a common measurement of comparison. Light water reactors and water reactors in general, we love to use things like cumulative CDFs, early release fractions, all that terminology that we have developed over the years that characterize the level of confidence regarding the source term, okay? But if I bring a gas reactor or a molten salt reactor into that conversation, and particularly if it's got a molten core, the game now changed. What do I compare? So those comparisons, which I expect are based on things like CDF and early release, okay, are useful if you're comparing, most useful if you're comparing like technologies. When you go to different technologies, then you go to things like, how far do I push this? And let me take an example that was discussed over lunch. In the high temperature gas reactor world, and NGNP a decade ago, we started a conversation with a number of companies, including Dow Chemical. And Dow Chemical's interests were, I'm burning my feedstock. They use natural gas typically for their source of energy in their plants. I want to stop burning my feedstock, and I want to use an alternate source of heat. So nuclear energy was very interesting to them. But they said, we got to go a step further. And the step further is not the classical safety case that you and I have been talking about, but the knock-on effect economically. If we have an accident and we have a co-located reactor to their facility, what's the potential damage? What's the threat to their $10 billion petrochemical plant that's sitting there? Okay, and they want that to be zero, obviously, but they want no threat in reality. The light water reactor, whereas it can fulfill all the requirements in regards to how we typically license reactors and the protective action guidelines, et cetera, okay, loses in that conversation because of the accident source term and the potential release that occurs. And hence it challenges their investment. So they would never think of putting a water reactor next to their plant for that reason. So there are other considerations I just wanted to put on the table here that have to do with why you might drive yourself down this kind of path. No economic consequences for severe accidents. And that translates to the type of thing that I just described to you, where not only do we want to protect the public, but we have a business reason to be, I use the word safer here, I'm not sure that's the right term, but to be less intrusive on the customer. And in their case, the customer is going to be co-located with them for the life of the plant. I mean, we're going to build our reactor on their land, and they can't get away from us, and we can't get away from them. So it's a marriage that has to last the life of the plant. Sorry.
Just a couple of quotes that make me think people will be really talking to. Roosevelt's famous quote about the known knowns and unknown unknowns. And related to that, for those who don't understand that, hindsight is 20% vision. And I think what we're talking about here is that the light water reactors, in a sense, are a victim of their own success, in the sense that a lot of the challenges we can throw at light water reactors are because we know them so well, and we've learned along the way where their pitfalls are, and then when the Davis-Bessel thing happened, or Fukushima happened, then we can say, oh yeah, well, now we know we can do better. And so, and I think, and again, the thing the Rickover quote is about, take reactors versus real reactors, so I'll just throw that one in there as well. But the reason I throw that in there is that when you look at the light water reactors, the bottom one is really interesting. You take the probabilistic risk assessment, and you list all of the potential failure mechanisms for a light water reactor, and you look at loss of coolant accident, whether it's a small break or a large break, like rod ejection accidents or reactor insertion accidents. You start from stacking them up, which one drives the probability of an off-site release and so on. You can then design those things out. And that's exactly, I worked on Iris with Westinghouse for a number of years, and that's exactly what, this was before SMR was even for an acronym we have. Iris was a small modular reactor we thought small modular reactors were really concept. And the idea there that we sat down over several days, several weeks, and basically designed out these potential faults. How do you avoid a small break hopper? Well, you don't have any pipes. You put everything inside a vessel, then you're going to get a hopper. How do you avoid rod ejection accidents? Well, you put the, you don't have any external control or drive mechanism, you put them inside, so you can't get an ejection fault. And so you can begin to do all those things, and then that's what actually drives the ability to, in fact, in the same way you say with NGMP, it's exactly the same context. And in fact, that's exactly what it is with Iris, where they were moving towards the ability to avoid the need for emergency plans. And that is something that then you can therefore put an SMR potentially next to a chemical plant. Or one of the things we're looking at in the UK, in fact, building a fleet of Irish reactors, so three of them next to the Sellafield reprocessing plant.
Right.
And that's a hell of a consequence if that goes well. Because Dow Chemicals is one thing, but next to a reprocessing plant, the reactor. But the reason I mentioned just all that is that I think that's the difference is that when you have got a clean sheet of paper and you have the knowledge base in which you can design things out, and that's the point here, again, for system or future system, you can design things out. If whenever you've got a real reactor that's actually operating, you're somewhat constrained by what you can do. And the point I was making earlier about the economics is you can always do something to an existing plant to make it safer. But that safer will come at a cost. Because your ability to, and this is where it's as low as reasonably achievable and as low as reasonably practical comes in, because you can always do something to make it safer, but are you willing to do so? So for example, if you go back to current reactors, shut them all down, completely change all the volume, the reactor internals, make them all safer, whatever that means. But that will come at a cost, and willing to accept that. So,
And that's the discussion in reality on the accident-tolerant fuel.
yes.
Okay? And, yeah, let's capture a couple of your thoughts in this discussion. Okay? One, economics will drive any of these conversations, because one thing's true, no matter how idealistic we may be in our thought process on safety, if we can't make it economic, we won't sell it, so it won't matter, okay, in reality. So it's got to be competitive against whatever you believe the competition happens to be. Number two, that's where I remember when I started this conversation a few hours ago, I said I disagree a little bit with Per. I wouldn't throw the light water reactors out. There's ways to deal with them to improve them, okay? It comes at a cost, and the question is this a cost acceptable? If I used a unitized reactor, whatever terminology you use for I put everything on the inside of a vessel, okay? There are downsides to that have to do with maintenance. The issue is, all right, then I got to convince myself in the process of design that is an acceptable trade-off for the safety improvement that I have achieved and done it in an economic manner. So as you look at advanced reactors, and you'll find that this is not a uniform opinion at all. And you saw it with Per and me, okay? Light water reactors shouldn't be out of this discussion. Okay, they are part of the body from my perspective with advanced reactors. The question is, can we achieve what we want to achieve, say along the lines of these kinds of objectives, okay, in an economic manner that makes them a satisfactory answer? Or is an advanced reactor, like my favorite, the gas reactor, or your favorite on molten salt, and Per's favorite on molten salt, okay, is that a better path? Okay? I think we need to keep our minds open to technologies, run through these, put the value on them, how much are we willing to pay for it at the end of the day, and how does the risk get described, and what risk are you willing to take, which I think goes back to your original question in reality. What risk am I willing to take? There's a concept of absolute protection versus adequate protection, which is not resolved, okay? And I don't plan to go into it here. But the issue is we have that constant discussion of how much risk is acceptable. Someone mentioned earlier building fossil plants. I think, I don't remember who brought it up. Building fossil plants has a fair amount of risk associated with it, okay? The effluent, which is more radioactive than a PW ever puts in the air, other than on accident day, okay? And the results of the combustion cycle, which end up in all these heavy metals, okay? It's a risk. And the question is, how do you balance those risks? As you go, and there's no absolute answer to it, but I think there's a starting point that if we agree the starting point is that we're going to fulfill such as protective action guidelines that we have in our fundamental aspects of regulation, are these the kinds of things that you want to satisfy? Are you willing to compromise on some of those to get the benefits? A salt reactor, for instance, has benefits thermally compared to a gas reactor. Actually, a molten salt reactor is better hooked up against a petrochemical plant than a gas-cooled reactor is because of the operational temperatures that it'll operate at, spread. But it has downsides of another nature. Okay, so it's a trade-off on these discussions. Other questions on these items? This can become a long philosophical conversation, which I don't want to drag you into. I want you to think about these. I want you to think about some of these lessons that we've learned here. And I've called this from a much larger presentation, and I've also culled it from the industry's much larger background. But as you pointed out, one of the reasons we can do what we just did here is because we know something about light water reactors. We've spent the last many decades operating them.
Just on that point, there is a very good, that is two examples, the gentleman just walked in everything for second one. But AP1000 actually has achieved exactly what we're talking about. AP1000 achieved improvement in core damage frequency, oxide release, compensation, and at the same time achieved that by dramatically reducing the amount of pipes, pumps, nuclear grade material, the concrete, the pipework, the whole kit and caboodle. So when you look at that list of items that's gone down in, that therefore has direct economic drivers as well as safety drivers. So the two can go hand in hand. And again, the SMR is another very good example of that.
Right.
And in fact, where the other thing as well is what I just got to think about, it's easy, and I can say this because I used to work more in reactors than in the fuel cycle, but I think the other thing to never forget is the consequence of some of these systems in a broader fuel cycle context. So, for example, it's no point having accident tolerant fuels if then that creates such a big problem for either the manufacturing of the fuel, which you have to go with higher emissions, or in fact you can't dispose of it, or if you want to go to a molten salt reactor, you want to come up with waste form where you can deal with the waste, there's still will be waste, it's not it's not a perfect incinerator. So again, it's just context, there's a broader context, and I'm going to point back to you yesterday. Don't just, and I think it's your point here, don't just think about what problem you're trying to solve. The chances are you'll solve one problem, but understand where the ripples are that you've created elsewhere. And that includes the fuel cycle as well as the reactor.
Very, very well. Now, let me summarize where we started. We didn't start in this discussion to establish a set of design criteria, or even design approaches. And this last slide brings us some of those kinds of thoughts, but that's not the reason we started this conversation. Starting the conversation back 2.5 hours ago was, how do we learn from the experience on the reactor technology that we understand the best, and how its decisions were made for particular capabilities and attributes of those designs, and based on those decision-making processes and how we got there, how does that influence how you approach your business going forward in advanced reactor design and development? That's the reason we had this conversation, not to question water reactors, not to question the specific issues, but do the decisions that were made that brought us to what we saw, how do we consider those decisions as we go forward and mature different technologies in this discussion? Any other questions, please? Sir.
So this isn't directly related to these key messages, but it's kind of a twist on this discussion. We've been talking about looking back on light water reactor technology as basically a window into considering how we can move forward with some of these new reactors. And I wonder if maybe you can talk a little bit about doing the same thing, but instead for the regulation side of things, because there have been, over the course of nuclear reactor operation, a number of changes in the way regulation was set up. For instance, dissolving the AEC and separating the fact that the organization was initially a two-mandate organization, both to promote and regulate commercial nuclear power, into two separate organizations like we have today. Can we look back on that and infer any lessons from that we can take forward in terms of either promoting nuclear power or better regulating it?
I promise I'll keep this within the next 20 minutes. This is a very long conversation that should give it full treatment, but let me touch on a few of the things. Your specific question about dividing the promoter from the regulator, okay? That was an important lesson, that we needed to do that, okay? Because we found ourselves with a lack of objectivity, basically. Okay? So that split was important. In concept, its implementation's a different problem, okay? What we ran into, and we haven't yet solved, are kind of a couple of characteristics. One, the Department of Energy today has never really developed its promotional activity and its support of technology development. It just has never done that as it can be viewed through the eyes of the regulator. There's movement today to improve that. There's some recent workshops that you may be aware of, which are for purposes of starting the conversation, where you say, okay, what are we missing? Okay, how do we move into the advanced reactor world? How do we regulate? How does the DOE play in that? The DOE's role has been poorly managed, because their role originally was to pick up the total aspects of the promotional activities of AEC, and that did not happen. Some of the promotional aspects of AEC remained within the NRC in reality, some of the work, okay? So we got that kind of problem over there. Another problem that in the implementation, and this is industry's drop, all right? And I'm gonna give you my view of it. Other gentlemen may have different views of exactly how it occurs. As we went through Part 50 licensing, does that terminology work for everybody here? We went through Part 50 licensing of the existing fleet. There was uncertainty as to what it was going to take to finish. I mean, that's real life. And so we drove towards a couple things. One, the one that gets lots of visibility is the so-called Part 52 license process, okay? Probably more consequential was that the industry drove the NRC, or collaboratively, it isn't like NRC didn't want to do this, to a prescriptive level that was a level of prescription that was not necessarily to ensure the result, but to reduce the uncertainty of what it was going to take to fulfill the requirement. Is that the best way to say it? Did I say that about right? Okay. It's a reductionist is the term that's used quite often. reductionist philosophy that said, now when I apply, I know what answer will work. I don't have to guess the answer anymore, okay? And so we drove the regulator in that direction as an industry from a very real standpoint. Today, as we go into the advanced reactor world, and I mentioned the pre-application work with the NGNP and high temperature gas reactor, and NuScale is entering that same framework with a little bit different thoughts, but the same thought process, where they want to change approaches to the way we have dealt with water reactor technology in their case, in my case, advanced reactors in general, and have the NRC change the thought process so that we get away from the prescription. I used the containment example with you earlier, okay? Manning of the control room, I believe that's one of the ones in the NuScale world, okay? What do we really need? And Para brought that up, okay? What do we really need to operate the reactor safely, okay? Questions, and the basis for emergency planning zone. Now the emergency planning zone is kind of interesting in history. You know, it's prescriptive today because we demanded of this industry to have a prescriptive reality, okay? But originally it was a compromise, okay? It was the folks that were comfortable and the folks that were uncomfortable, and we said, oh, if we make it about this and make it about that, in the emergency planning zone, it isn't technically based, okay? It's based on a judgment of what will provide sufficient margins and protect the public in the event that severe accidents should occur in a water reactor, okay? We could justify less than 10 miles and 50 miles for a current reactor. I'm talking dose pathway, congestion pathway. We could justify that even for existing reactor. Nobody's going to take it on. But I believe, and confirm this for me, NuScale is in that conversation today, correct? Okay, you're taking that on. And we have in the gas reactor world taken that on specifically. I talked about it in terms of containment, fuel, but I'll talk about it in terms of emergency planning. We essentially have taken in a very similar thought process to NuScale and said we want to eliminate the emergency planning zone, just eliminate it. Okay, and we could do that for the following reasons. Again, I won't go through all of them. We can do that for the following reasons. So, if I go back to your question, the aspect in regulation today is we've made our bed, and we've got to, we have to deal with it. All right. Now we're trying to undo it. And we're trying to undo it and go back into a world which allows more freedom of establishing technical requirements and have a framework, however, that allows the NRC to do the job that they're paid to do. Their job's important. And they have to be able to gain the confidence and protect the public. That's the structure we work in, okay? If we lose that, and by the way, that's been lost once, okay? That was lost with the Millstone plant in, that's Connecticut, I guess, Connecticut, okay? And we lost that confidence on the part of the public and the NRC, and it cost a tremendous amount of money to reconstruct that. Okay, so we want to maintain that confidence of the public in the NRC as the watchdog of what we do. At the same time, we want flexibility. So we're going to move away from the prescription. We have to justify what we want to do. We have to work towards this framework, and I mentioned the effort that's going on with Southern, and the specific efforts that are going on in NuScale and have been going on previously with NGNP. Okay. Now, how close, excuse me, go ahead.
Well, I'm just thinking, as you're talking, there's historical context here. If you go back to 1960, and the ABC said, let's have a demonstration program. So we'll build an organic moderated cooled reactor, we'll build a sodium cooled reactor, we'll build these different kinds of reactors. And within 5 years, they were built and operated. So they designed them, they licensed them, they built them, they operated them, and for a very short period of time. That's inconceivable. And it goes to the point you made, which is exactly right, that industry went into the AEC and they didn't know what it was going to take. And it made them incredibly uncomfortable. What we had on the other side was people who were pretty competent and were willing to make judgments, and they get in the room, this looks okay to us, go forward. And the industry was so challenge process.
Right. And so we're undoing that now. And the folks that are in this conversation that have been around a while in NRC understand this discussion. The larger body is having a hard time, of staffers is having a hard time coming along. It's just going to take a while to get through. We're not, you said it's impossible, and you're right, to go build a bunch of reactors in demonstration mode. We had national imperatives, national priorities to go do those kinds of things. In the naval program, we had this debate going on, should we use sodium-cooled reactors or should we water-cooled reactors? Well, how do you answer? We build both. We build a prototype, we build a ship. Okay? We didn't like the answer at the end of the day on the sodium-cooled reactors, not because of water reactors, by the way, okay? Just, it was a maintenance headache, okay? So we couldn't deal with it, okay? In the environment that was important to a weapons platform. Remember how we started this conversation? It's a weapons delivery platform. That was its purpose. It wasn't to be an R&D platform or a breeding platform, or a burning platform. That wasn't its purpose. So, but that took a lot of money, a lot of the treasure of the United States to go after the examples that you gave and the examples I just gave, to go do it that way. I don't think we're going to see that ever happen that way again. I agree with you. I don't think that'll occur. Okay. Politically, no, I just offered opinion. Politically, the discussion is this is a mature industry. Why do we need to foot the bill? You know, you've heard that before. But just the reality is we don't have that kind of money.
Just want to add perhaps a thought to the process. Some years ago, I was instrumental in starting up a small company. Herb talked about the FDA in his presentation, what it takes for the FDA. This company had to do with plastics in the food industry. It had to have a okay on the FDA, so there was an application. Normally, the FDA process takes 5+ years. But somehow we figured out how to do it in a much shorter time. So what we did is we were dealing with chemicals, essentially aromatic hydrocarbons, which are terrible in terms of health effects. But our process was the following. We tried to anticipate not what the FDA would require, but what we thought they should ask us about these particular things. So the first thing we did is we made a complete case so that when the application went in, everything that we knew the FDA were going to ask, we had all the references, everything, so the examiner literally did not have to get out of his chair to check out, number one. Number two, we anticipated the questions we thought they should be asking us and answered them in advance. And number three, we realized that we wanted to put the application in August. Why August? Well, the end of the fiscal year is September. And one of the, let's put it this way, the FDA examiners, they review in September, and people ask, what did you approve, what did you do this year? So we sent in an application 4 weeks in advance, and had all the questions answered. All they had to do was rubber stamp it, and out the door, and we got our approval in 7 weeks.
Now, he's told you there's two very important points. The third one's kind of humorous. Okay?
But it worked.
But it works.
You got to remember that there are other unwritten things that you have to deal with.
It's real life, and that's all part of managing design activity. Any questions? We've thrown a bunch of stuff around today.
My opinion on that, any questions. And the first one, you said that lots of the case studies that we've looked at before as well, they came from unexpected needs. So, is there any way that we can use some kind of more contemporary simulation of human effects. So not looking at an engineering simulation, kind of, let's run through some possible human effects that could happen to a system and see what that happens, from using some kind of code or something like that. I was wondering if that's something that's done as possible, looking at human effects, not engineering effects.
Let me flip the question. One, I'm not at all expert in terms of your direct question, but let me flip on what we did do. Okay. The way the operators were trained in the 70s and early 80s was basically event-based. I'm going to train you on an accident. The accident is a loca. What indications are you going to expect, and how are you going to respond? Okay? And that went on for all the things that might occur. The result of the TMI-2 accident was kind of the driver to it, but it was already in motion. And that said, let's go to symptom-based thought process, where we're not going to try to predict what the event is that's going on. What we're going to do is use plant parameters that suggest to you what might be going on, not to tell you what the event is, but what your response should be to the events, to the indications that are available to you as an operator. So we took the operator out of this mode of try to guess what the problem is, and put them in the mode of respond to what you see, and gave him some fundamental thought processes of what he has to control. I got to control reactivity. I'm dealing with water reactor now, so I got to deal with reactivity. I got to deal with inventory, water. Okay, I got to remove decay heat. Okay, very fundamental thought processes where he looks at the plant indications, what they're telling him, and how he assures that those fundamental requirements are fulfilled, and got him out of this discussion on events. Okay, because we found the event training was a failure in reality. Because in TMI-2, as an example, in the accident in TMI-2, they were looking for the event. The answer is all they needed to do was look at the indication of what was going on and know which indication was valid and which indication was not. And they failed, and I don't mean this on a personal failure level, but they failed to recognize what the indications were telling them. The indications were all there. There was no magic to this discussion. But they didn't interpret it correctly because they were dealing within how they had been trained. Now, if I go to your question, which I can't answer because I don't know the answer, okay? Are there ways that human response or potential human response has been modeled that you could factor in? I don't know the answer.
Just to add something, for example, that the one we said with the keys.
Yeah.
So that's not, the other things, look at events or indicators, that's all systems analysis, or is that losing the keys?
Well, that's a very interesting one. I would expect, if I went to my PRA gurus, okay, some of you may be there, and said, would you have evaluated the effect, the equivalent of the effect, of the guy throwing the keys and dropping them through the grating, and what that would have meant? The answer is, I don't know the answer to that question. Anybody have an opinion on that works in that world?
I don't believe that. I think we remember hearing some talk about doing PRA on human behavior. I don't remember who exactly was doing that, but I do remember recalling some talk about that.
Well, I think it's a good question, and I would suggest you pursue it because it's in terms of risk analysis. The human element, whether they model the keys, is a different issue, but the consequence of something like that, okay, is very important in terms of acts of commission and acts of omission that the operators may involve themselves in responding. Okay.
That's fairly routine.
Pardon?
That's fairly routine.
Okay, and I just don't have that knowledge. This item, I changed pages on you, but that item here on the operator action not required, or avoiding the operator being able to do some mischief, if I may be loose about it, in the process, is intentionally trying to remove that element because it is a highly variable element that depends on fitness for duty. I mean, I don't know if that's a term you guys use, okay? Yeah. An operating plant You know, did I have an argument with my wife? Okay, are the kids sick and in the hospital? Did I have a drink? Is that before I came to work? You know, the whole 9 yards of fitness of individuals for operating a plant, okay? That brings a series of uncertainties in such a conversation that make you not go after the specific action, but after how do I envelop the consequence of acts of omission, acts of commission on the part of the operators. And those folks that are more familiar with that, how that is done, I'll leave it to them and would ask that you pursue that. Do the INPO folks do that today?
I don't know. I think not. I don't know.
Yeah, well, and we can find out. We'll find out for you. Sir?
I know that INL has, it's called a human system simulation lab. They do all sorts of things like they quantify like situational awareness to see if automation makes people kind of like forget what they have to do. They use like eye tracking glasses to see how they look at the screen and everything. There's a facility that Virginia Commonwealth University is involved with in Virginia, and then the real like world class institute is the Halden Reactor Project in Norway. They have a lab, CAM lab.
We've
And,
been.
Yeah, okay. Yeah, and the NRC actually uses that lab in Norway as well for human factories.
One of the contributors, and this gets to the instrumentation question, one of the contributors to some of the actions that we observed in the TMI2 accident as an example, or Davis Bessie, had to do how things were presented to the operators. What does the instrumentation indication actually mean? Okay? They looked at the tailpipe temperature, for instance, on the pilot operator relief valve at TMI2. And it read saturation. Well, the answer is, of course, it's going to be at saturation. It's an open tailpipe into the atmosphere of the containment. They read that as the valves closed. They didn't understand the indication, what it really meant. Okay? And we fail as engineers to provide them with knowledge in that case. In other cases, indications that truly tell them what they need to know. And that's a real challenge for those of you in the instrumentation world, is how do you get to information that's actually useful to the operator to interpret what is going on in the plant so he can use the symptom-based procedures and get to the right answer. Okay? Very important area. I expect that's part of what you described. It goes on at INL. I just haven't been part of that conversation. Other questions, observations? It's 4:30. No, go right ahead.
I have a main question. This comes from, I think, a bit of I can't say this politely, but like a slight weakness on my part, I think, or stubbornness. With sodium, with introducing sodium. You know, can you say something to reassure me that will, you know, isn't widely used? Is it just that the sodium reactivity just makes me slightly recoil?
So you're not in favor of sodium-cooled reactors at all?
It just makes me recoil. But I know it's just a gut emotional reaction. You know.
Yeah, I mean, I run a simple test in my mind, okay? And this isn't the same one you're running, I don't think, but let me. One of the questions, and this is, I'm not an operator, but I've spent years and years in operating plants, okay, in an engineering management function. What is clear to me is the operators want to be happy with the result of their coolant leaking onto the floor. Okay? So if you look at it and you say, because I started one of the conversations earlier today, everything leaks at some point. Okay? The issue is, am I happy with the result? Water leaks on the floor, I get some activity. Gas leaks on the floor, or not leak on the floor, gas escapes. Am I happy with the result? If molten salt leaks, am I happy with the result? I mean, that's the issue. Is one of the tests is operationally, is the consequence of what really happens in a plant, in a real mechanical system that leaks, not a lot, it leaks a little bit, okay? Is that an acceptable result? And that has to be one of the questions amongst a lot of others that you answer. Are you happy with it? Now, sodium, when I put it in the submarine and it leaks, life gets a little bit interesting in a hurry. So I don't like that particular answer because of the environment it's in. It's not fundamentally anything wrong with sodium in that case, it's just, all right? And as I mentioned earlier, the maintenance issue in the naval environment was not the sodium-water interaction. However, it was the fact that I can't keep the plant hot. Okay, I have to keep the plant hot, and molten salt has that same need, okay? And does that work for the environment I want to operate that particular reactor in? Is that convenient to do? And on the submarine, which doesn't have a very long extension cord, okay, and certain limited capabilities to generate power, okay, if the reactor shuts down, how do I keep things in the condition I want them in? Okay, so again, it's the environment. The environment you're in, it could be a satisfactory answer if you were in a land-based plant. You know, I won't comment on technology in particular. You know, there could be an acceptable answer. I happen to like benign coolants. That's my personal like. Okay. Other questions, please. Sir.
Just wanted to add to that, sort of going full circle really. Mark, you said, I accept your opinion, you don't like molten salts. I do, and I know some other people in this room, not naming names, like to do as well. He put his hand up. Okay, sodium, alright. Anyway,
we're going to line everybody up against the wall here.
The point I'm going to make here is that actually, like, you've got a slight personal opinion on something that you've got from somewhere, like everyone else has got their own personal opinions. Now, going back to the whole regulatory thing, new ideas and new opinions on safety, going through the human system, everyone's got a slightly different opinion. It's going to be so difficult to get everyone on the same playing field. To look at something objectively and say, yeah, that's safe, the next person will go, well, I don't think it is. And then you're back to square one again. So I think this whole idea of actually getting a new reactor, and this goes back to the stuff we talked about yesterday, getting a new reactor commissioned and getting it through the regulatory commission is going to be really difficult.
One, it's difficult. One argue that it's difficult. However, that's what we get paid for. Okay? That's what we get paid for in our careers, is to take on those challenges. You know, let me give you rather than dealing all in the technologies, let me take our favorite plant again, Davis Bessey. I want to go operate, you know, I was hired in as a part of the management team to recover Davis Bessey in 1985. Okay. We had many of the same things you just had, not because we didn't have a licensed reactor, but because we had a reactor that could not fulfill its license. Okay? And how do we deal with the changes that are necessary in a way that didn't break the company in the process? And how do we make compelling arguments that the technology, the way we have now modified it, changed it, maintained it, whatever the issue happened to be, okay, that it is an acceptable position to ourselves, and once we get ourselves convinced, I usually don't find the regulator is my problem, okay? It's once, you know, your point earlier, once I'm convinced, the regulator is not usually the issue, okay? The regulator only becomes the issue in the sense when we have to educate them on something that's new, and that just becomes, that's just a time process, okay? Because they're no different than the group here, okay? They're folks with technical backgrounds, varying capabilities, and it just takes time to educate them into newer paradigms. Okay. So, interesting opinion. I'll just let the opinion go. Interesting observation. All these technologies are very interesting rather, and they have to be allowed to mature to the ones that remain credible, and then see how far we should take them and move them down the road. And don't lose sight that water reactors can be part of that conversation as well. I thank all of you. I appreciate your participation in the discussion. Good luck with your 2 weeks here.